In this course, you will learn how to create an AI that can dominate the game Space Invaders. But the system we built to do this uses an algorithm that also crushed the games Mario Kart,
I didn't get hit by that. That was
Mortal Kombat,
Fight.
and Super Mario Galaxy. The best thing is that the system is built around the Godot game engine, so you can use it to train AI for your own games. Godot is completely free, and the programming language it uses is basically the same as Python. In the course, we train multiple AIs. Each of them sees the game almost like a human would. To make sure this works, we will look exactly at what the AI will receive. Another important thing is that you don't need to have a machine learning background, and we almost need no theory. We just cover some simple concepts like rewarding the AI to behave more like we want it to, and other basic things. In order to really understand our experiments and explain what is going on, we will also learn about a popular data science tool for managing AI training. To support this, I will run more and long experiments than you have to. So we have enough data to analyze. Because getting a very strong AI could be done relatively fast, without much hustle or hardware needs. Generating simple graphs doesn't only look fancy, it will also help us to spot progress that would be almost impossible to see without any statistics. After completing the course, you should have learned a lot about training reinforcement learning algorithms for a game or simulation, and should be able to apply our modular system to other projects too. Here you can see the game plan. It starts with a random baseline, because without it, it is hard to judge whether our AI agent really learns something. Then we just use simple rewards before testing any wild ideas. For example, +1 for shooting an alien, -1 for losing a life. Having the simple agent first makes judging advanced changes easier later on. This is important because we need to know if we're doing more harm than good by manipulating the agent. After that, we try more interesting things, like negative rewards for missing shots, and so on. On the left, you see an agent that chooses his actions completely randomly. The agent on the right was trained on my potato laptop for about 20 hours. It is using the BTR algorithm, which we will cover briefly at the end of the 3 modules. With better hardware, the AI would of course learn faster. But since the AI has to learn to see, while also learning to play the game, it takes some time. The first algorithm we are using is called PPO, which is basically the hello world thing in deep reinforcement learning. The cool thing about PPO is that you can train an agent to win some games, even with an old laptop that has no GPU. All you need is some patience. However, the Beyond the Rainbow algorithm easily achieves a high skill level. I also want to note that switching algorithms is really easy with this setup. So don't worry if you prefer a different one. The setup needs are pretty simple. I tested everything with Windows 10. That said, it should work basically everywhere, even on a potato of a computer. Anyway, enough talking around, let's start with downloading the game first, so we don't get bored. We will use the game Space Invaders, which CyberPotato implemented in the Godot game engine. Check out his channel, he also has lots of other great videos. In this playlist, there are also lots of other games. Not all of them have finished game loops, but that shouldn't be too hard to add. The link to the playlist will be in the description, and there will also be other relevant links, like the link to my Git repository with the finished project, or the link to my school course, where there's more of this stuff. Anyway, we want the Space Invaders
right here. So
game. If you want to download the game from his repository, you can do this here, but the original game code is also available in my project repository. Anyway, let's go to code, download zip. I already have a folder prepared with the download, so you can move it to any folder you like and then just extract it. If we then click into the folder, we see there's an extra folder with the same name, and then there's the game. So if you don't like this, you can just move it out from there. So we also can delete this. Then we can download the free Godot engine. You can just go to Google or use the link in the description. However, I don't know if future versions of Godot will break anything. Maybe if they make any really big changes to the engine. So you could download the latest one, but if you want to be sure that everything works, you can go to previous version, scroll down to Godot 4.6.1 and download the stable one. Although I think every 4x version should work. As I said, I tested everything on Windows 10, but it should also work on Linux and macOS. Anyway, I already downloaded it. So we can unzip this again. And you probably should move it into a program folder or something. It doesn't really matter. The cool thing about Godot is that it does not need to be installed. You can just double-click the executable, ignore this warning, and then the engine already opens. You can also do a right-click on the executable and pin it to the start. So if you do this, you can just start it from here and don't have to search it every time you want to open it. Anyway, we can now import the game. So we open the engine and then we need to import it. If you're really lazy, you could just go to the Space Invaders game we just downloaded and just copy the path here. And if you press import, you can insert it here, press enter, or you would just select it and find it manually. And then what you need to do is to click on the project Godot thing and import it. This is no problem. Great, here we are in the project. First things first, let's start the game. You can do this by pressing the play button over here. And if you then use your keyboard and press space, everything should work exactly as here. You can also pause the game right here and execute it frame by frame. If you look on the rockets, you see they move every time I click. This will be really nice later on if we are debugging stuff. All right, now I would just close all scenes by pressing the middle mouse button. Then we can make the sidebar smaller and only open the main scene. You can do this by going down here and either search for a main scene, or you would just search for it by typing it in here. If you double click it, you should see all the nodes that are in the main scene on the left side. And then you can switch from 3D to 2D. And by pressing the middle mouse button, you can move this around. So optimally, you already have a little knowledge about Godot. If that's not the case, don't worry. I explain everything very slowly. For the case that you need more guidance, I will also provide 2 links to great Godot tutorials in the description. Anyway, here is a 5-second explanation of the main thing you need to know. In Godot, everything is an object, which is synonymous for node. The term scene just means a certain group of nodes. Scene can of course contain other scenes, since everything is just a node. For example, we are currently in the main scene, and every clapboard icon you see here on the left is its own scene. For example, if you click on here, see nothing, but a tab opens just like in your browser. If we click on the player scene, we see just the player. So the main scene just contains copies of other scenes. And for example, this bunker scene you see here is just copied 4 times. So if we would go into it and then, for example, change this thing, save it, and then we go back, we see that all of the copies have changed, which we don't like. So we can go back into the scene and revert this change, save it again, and now the game looks fine again. Furthermore, you can also, next to this icon, there is the script icon, which takes you to the code of the node. And if you want to go out, you can just press the 2D at the top or go back. Awesome! Since you now understand Godot perfectly, we can move on with the tutorial. Let's start with a quick explanation. In reinforcement learning, there's quite a lot going on. There will be many moving parts in the pipeline, and each part can break, just like in a car. Sometimes there are even silent problems that don't cause an error, but still ruin the training. Those can be very hard to spot, and we will deal with some of them in this tutorial. The best way to prevent problems is to visualize every important part, which does not need to be complicated, but can still feel like unnecessary work. If you have never been in the situation that you debugged a problem for days that could have been prevented easily. Anyway, to be honest, I enjoy visualizing things, as it's nice to see what's going on in the pipeline. So just remember, slow is fast and fast is slow. We will use a plugin that helps with some of the quote-unquote visualizing. So in Godot, you can easily install plugins by going to the asset lib at the top. And now we type in imgui. This one, and just download it. This tool is also used in other programs, so you maybe already know it. If it is installed, we also have to activate it. For that, we go to Project, Project Settings. And if you work on 2 screens or on 1 screen, it could be that the project settings is hidden somewhere here. This is because of the way the project was saved. I think you should be able to find them and just draw them in here. It's a bit annoying, but yeah, now you know. Then in the settings, we go to plugins and just click on enabled. Great. imgui is not strictly necessary, but I highly recommend it for the reasons mentioned before. Anyway, let's start with finding the player code. It of course depends on the game, But normally you have something like a player, which you want to be controlled by the AI. You can go to the scene, but what we really want to do is to go to the script. So we can start with visualizing the player actions that are given by the human without any AI thing going on. So this process function is called every frame, and we will later on let the agent take control of the player, but for now we will just insert our functions here. I think you will understand it in a second. Let's just create a new function at the bottom. We can call it activate imgui. It will receive correction from the vector, and then we do pass. Then of course we also need to go to the process function and type in what we just written, activate imgui, and it will get the direction variable. So when the player presses a button or no button at all, it is stored in here. And this is what we will be visualizing, and later on will be controlled by the AI agent. imgui has lots of functionality. We will be using very simple things from it. So what you normally do is you type in imgui, type in begin, and then we can give it a name, visual inputs. We also need to end the call. For example, if we want to print something, we just write text wrapped some test. And if we then start the game, we should already see the box that prints it. Okay, this also was hidden, so maybe you have to search it again. But basically, then we get this box. We can move it around, size it, and it's stating our text. Anyway, we don't need that. We will just define a new variable for visualizing the actions. If empty imgui crashes, then what we just do is if direction 0 equals -1, we set the action name to move left. And by the way, if you want to look like what these vectors look like, you could print them in the console, or just control right click and then you see the descriptions here. So, and maybe we should close all of this by pressing the middle mouse button again. Okay, so the other things are probably self-explanatory. If the direction on the left position equals 1, we say move right. This needs to be an elif. And otherwise, we say don't move. Then what we need to do now is to just write imgui text wrapped and provided our action name. I also want to show you how the vector looks like. So we convert it to a string and write it as well. We now start the game. We see that I'm not pressing any button. I'm going to press left for the A button, moving left, and it's saying left. And same thing for right. So this is working great. All right, we can delete some lines. And by the way, I'm pressing Ctrl X or Ctrl C or Ctrl V without marking the lines, and Ctrl Z and Ctrl S. I will probably have them in the descriptions, the shortcuts, if you're wondering when I'm jumping around quickly. Anyway, you probably noticed that we visualize the moving, but not the shooting. So let's tackle that. So if you look around in this script, you won't find the shooting. It is placed somewhere else in the code. And it's placed in a way that makes sense. But if you want to find it out yourself, you can pause the video now and search for it. Okay, so it basically could be anywhere in the scene, in the whole scene tree. But of course it makes sense if the shooting is handled near the player. And it's basically here in shoot origin. You could also have tried to type in here shoot and would have found it. You wouldn't have found it that way. Anyway, in the shooting script, it says input and action just pressed. This is the thing we are looking for. By the way, if you are unsure about the input map, so about which button to press for which action, you can go to project settings and there is the input map. So for example, shoot is the space button. We can make this an exercise. So if you want to try it yourself, you can just do the same thing as we did before in order to visualize the shooting. If you are a bit lazy like me, you can go back to the player script and just copy the whole function we have written, as well as this one, and then go back. And I have the clipboard history on, so Windows V gives me that, so I can just select everything. Maybe you ran into a problem where you couldn't get anything to be visualized. This probably means you forgot to write a process function. So this was a bit tricky because this input function is only called whenever an input is pressed by the player or so. Anyway, now that we have that, we don't need an input in this case. And which means we have to delete it here as well. And we can delete all of that for now. The action name is now just not allowed to shoot. And if the can shoot variable from above is activated, which is this one, we can say action name allowed to shoot. And of course, otherwise, we are again not allowed to shoot. Then of course, we have to write it to the box. Guide, text, wrapped, loud. Action name. Now, if we start the game, we see we are not allowed to shoot, and if we shoot, we are allowed to shoot, and if we shoot, we're not allowed to shoot, as long as the rocket is in the air, because that's just how the game works. It would also be nice to see whether the player pressed the shooting button. So we will basically just visualize this thing here as well. For that, we can delete this line and define another variable. Let's call it shooting pressed. Shooting pressed. And if input is action just pressed, which takes the shoot argument from the input map, then we do set our variable to shooting pressed, and otherwise we set it to shooting not pressed. Then we also need to write this text. With the right variable. We now start the game. We see we're not allowed to shoot, we have not pressed it, and if I press it, it does not work. But if I press it more often, we see that it's kind of flickering. And I think the error lies in this function. So if we press Control left mouse and read all of that, it says it will only return true on the frame or tick that the user pressed down the button. But the way, so the if is like true for 1 or 2 frames, then we see it's pressed, but after that, even if we hold on to the button, it is not pressed anymore. If we go back to the docs, we could search for a better function. For example, is action pressed? Looks good if you're pressing the action event. This is exactly what we want. So we can just delete the just. And if I try it again, then I'm pressing the button and it's also saying I'm pressing the button. I'm releasing it. Great, great. Anyway, we can now visualize all the inputs and all the actions the player is taking, which we did in the shooting and in the player script. Maybe I have not mentioned it, but we will move it out from here and move it into a different script later on. Then we will also start with a random agent, so to say, but I'm getting a bit ahead of myself. Because this random agent needs a few other things for it to make sense, which we will deal with in the next module. Let's talk about Godot AL agents. This library is what makes training AIs pretty easy. We can go to the asset lib and type in Godot AL agents. And then there are actually 2 links. This link is where we get the files from, and this link contains some further descriptions. We will not use the download button because I think the version here you get via the download is outdated. Anyway, the right download links will be in the description, but if you want to have a look at more of the information, you could just open the link. And yeah, here's some information about the plugin. There's also a trailer. And this repository also contains some example repositories. For example, this full FPS. Anyway, we want to go to view files. And by the time you see this video, and even now, the version already has changed. So if you want to download the exact version that I used, you can go to commits or just use the link I will provide to you. And I used exactly this version. Browse files. Anyway, we can go to code, download the zip, and then we don't need to move it around. We just need 2 files from there. So we extract it. And what we need is this and this. So by pressing Ctrl X, we cut it out and jump to the folder where you have the Space Invaders game. In the Space Invaders game, we go to add-ons. Here you should already see the imgui, and then we copy those two folders, which was a little messy, sorry. So actually, we need to go into the add-ons folder and take the plugin, move it out, place it here. Then delete this empty add-ons folder and cut out this folder. So the script templates need to be at the same level as the project Godot file. Once that is done, just make sure everything is nice, looks good. Go back to the project. And actually, we also need to activate this plugin. By the way, this 0.1 is false because we downloaded it from the Git repository. Let's talk about the key thing in training reinforcement learning agents. Training such an agent takes lots of time. Using multiple instances of the game in parallel massively reduces training time. And equally important, the agent itself sees multiple stages of the game at once. So starting, struggling, winning, and so on, instead of learning on a tunnel vision. Training simultaneously in different realities prevents the agent from overlearning a single scenario. In short, data variability and variance are increased. The Python library Godot RL agents provides several options for parallel training. First, using several instances of the exported games at once. Second, using several instances in one game at once in one executable. And the third is a hybrid of 1 and 2. We will use option 1 because it's just easier and quicker to set up. Alright, since we want to use option 1 of parallel training, we need to do a little trick. This basically means we are creating an AI main scene instead of having a reset function in the game. Creating such a function can be quite some work depending on your game. But with this AI main scene trick, we can easily restart the game without having to reset every tiny thing that is going on in the game. In Space Invaders, this is only alien count, player position, lives, and so on. But in other games, it could be quite a lot. Basically, what we want to do is to go to the Scene tab, create a new scene. We will take another node and create it, because we don't need to hold any images in this node. Then you can save it by Ctrl S, and we call it AI main. Then we can add some nodes to it by pressing the plus button here. The first thing would be the sync node. And if you have the RL agents plugin properly installed, you should be able to see it here. The second one is also from the plugin. It's the AI controller 2D. So what the sync node is doing is that it's handling the communication between Python and Godot. You don't even need to look at its code. You could do it, however, but quite a lot going on there, which you don't need to touch basically. And the AI controller node also has a big script in it, which you also don't need to touch. But we will add our own script that basically uses both of them. Anyway, for this to work, we need an autoload. An autoload in Godot just means execute this no matter what. So normally when the game starts, the main scene is executed, and then everything that's in the tree under it will also get executed at some point. But an autoload is always executed. Creating it is pretty easy. We just go to the project settings. Then in the globals tab, or sometimes called autoload, we can go here to the path, select our AI main scene that we just created, and press the add button. The name AI main is fine, but we could move it. The next thing would be to create a script that inherits from this AI controller script. So for that, we click on the AI controller node, then we click on the extend script button. And in order to differentiate better between the two, we will just call it my AI controller. And the rest should be fine. To make our lives easier, we can go to this link, it will be in the description, and basically copy this template script by pressing this button. Then we just paste it here and delete everything we don't need. Basically, every one of those functions needs to be overwritten for the plugin to work. Awesome. Now we are at the point where we can make use of Python. So this will be discussed in the next module, but if you still want the game to work, you can go to the sync node, and on the right tab, you can switch from training mode to human mode. Then basically everything, the sync node, the AI controller, everything is deactivated and ignored. So it still works to start the game and play normally, at least in theory. Maybe you were able to spot the problem, but the thing is, we need, of course, to inherit from the AI controller. So now it should work. Awesome, even the imgui is still here. So the way our whole setup works is that it uses a Python script to take care of the agent training. This Python script sends the actions that the AI agent wants to do to the Godot game and receives some data in return. Most importantly, it receives downscaled screenshots from the game. So our AI agent actually sees the consequences of his actions. Instead of screenshots, we could also use simple unstructured numeric data, like position, health, etc., or even use raycasting sensors. But I find that kind of boring. So we let the agent see what we see when we play the game. Python can also send curriculum learning information. I will cover this in a course on my school, but it's basically a way to increase the difficulty during training and learn skills progressively. Now we need to install Python and a few packages, which is kind of the boring part of the course, but don't worry, If you have never done this, I will make it as easy as possible. You could just install Python normally and use your normal terminal. That said, the more convenient way is to install miniconda, which comes with its own terminal. This tool is quite popular in data science, as it helps you to easily manage your code installments, and it's only about 400 megabytes. The link will be in the description again, and then you can go to the upper right, download, keep the registration, and download it for your operating system. As I mentioned before, I tested everything on Windows, but almost all the commands should work the same in Mac and Linux. We can install it just like a normal program. For me, it says it is not empty because I have already installed it. So I will temporarily choose some wrong path. Or maybe not. Anyway, you click install with the standard options, and then we can continue. All right, I would recommend to pin it to start or place it somewhere to quickly find it. And if you open it, it kind of looks like this. Except for this clink part, which is just a convenience tool, so you don't have to remember all your commands. Anyway, this is where you will install some Python packages, and we will also start the training from here. But before that, I recommend you to install clink, which you can just do via this link and then download the executable and install it like you installed miniconda. It is not necessary, but it's for convenience, as I said. Anyway, the main reason why miniconda exists is to have different environments. This just means if you have different programming projects, you can have different installments. If you, for example, need different versions of Python or other stuff. So the first thing we need to do is to actually create an environment. This is only done once, and then we will use it. Conda create link is already suggesting the command I used, and I think I need Python 3.12 and nothing higher because of the Godot RL agents library or something. I will check this. Anyway, this can take a while now. And maybe when you did it, you got something like this, where it asks you to accept the terms of service. So you would just write accept, and then it should be fine. This will install a lot of stuff, but we need it. I will pause the video and continue when it's finished. The next step is very important. We have to activate the environment. Activate tool every time you restart the terminal, you need to type in this command, or otherwise the terminal will not use our environment. And the way you see that's activated is on the left, it currently says base, but when I press enter, it says school environment. All right, the next step will be individual for you. That said, dealing with Python libraries can be a bit of a mess. So I tried to explain everything below in the module description. If you still run into issues, feel free to use the attached community post to ask questions, or use the Claude large language model. It's pretty good with such things. Anyway, if you don't have an NVIDIA GPU, it's quite simple. You just type in pip install torch vision and press enter. If you do have an NVIDIA GPU, you will type in NVIDIA SME, and then it should show you your GPU. For example, I have GTX. But what you are looking for is this, the Godot version. I have version 13. So you just remember this number and then go to the PyTorch page. Link will be in the description. Then you select the PyTorch build you want. It's the stable. I'm on Windows, so I select Windows. Then we use pip and Python. And then if your system says Godot 12x, you pick the highest 12x version available on the site. However, I had Godot 13, as you saw, and still picked Godot 12.6, so it's maybe not that important. Anyway, then you get the command, which you can copy if you're able to, and just paste it here. If you're on CPU only, this will be quite fast, but with a GPU it can take a while. And if you don't have an NVIDIA GPU, don't worry, the PPO algorithm we will first cover still works without it. And the Beyond the Rainbow algorithm would also still work without it, but I haven't tested this yet. Anyway, I will pause the video now and continue when it's finished. By the way, if you don't have an NVIDIA GPU, it could be that you are lucky, because it's not it's recommended but not required that you have an NVIDIA GPU, but that the support for other GPUs is a bit tricky. Awesome. Now that is done, we can install the next stuff if there isn't an error or something. But before that, we can quickly check. Okay, I somehow crashed my terminal, but that's no problem. Just activate the environment again. And then quickly test whether Torch worked. So what this command does is it imports Torch, If that already gives an error, then the installment did not work. And then it prints the version. And it will also print if CUDA is available, which basically means if your GPU can be used. But if you install the CPU version, this will just print false. Perfect. So we have this version and the GPU works. By the way, if you want clear the terminal, you can always type in CLS and hit enter. So the second to last thing we need to install is pip install Godot clean. What this does is it's the counterpart to the Godot plugin because we also need the Python version of it. And what this does is taking care of the reinforcement learning. So it's a library that provides high quality single file implementations, and the Godot library also and plugin also provides alternatives, but I recommend clean because it's the most simple to use. And I also implemented the PPO algorithm and the BT algorithm for clean. So I did not implement it myself, but I adopted it. But more on that later. The next thing we need to install would be clean this mess. Imgui. This is just for visualizing our images or game screenshots. Awesome. Now we should have everything installed that we need for the PPO algorithm to work. If you want to have a full look on my environment, I can call pip freeze, but you don't need to do that. Later on, when starting the training, I realized that I forgot to install these two packages. So just quickly do pip install GPU util and pip install ps util, and then you should be good to go when you want to start the training later on in the course. In this module, we will cover the basics on how to use the terminal to start the training with Python. As I mentioned before, Godot agent supports 4 different reinforcement learning training frameworks. We will use clean because it's the most simple and friendly to use in my opinion. If you click on clean, we get a description, which is the same as in the official docs. In debugging, there's quite a number of algorithms. If you click on the overview, you see the implementations in the table that this library provides. We will use PPO because it's the most popular one, but if you scroll down, on the left, you see the rainbow algorithm. Later in this course, we will talk more about its descendant. Anyway, let's go back to the plugin page. Here you see some examples on the basic usage. We will start with the most simple one that just starts the training with no extra commands. But there is also the possibility to export the Godot game into an executable and use this one. So for debugging, we will start it from the editor, and for the real training, we will use exported environments. Then there is also the option of having more exported environments in parallel, and of course to speed up everything, and so on. What we will do now is to download the example file and start the training. The links will be, of course, in the description again. This, of course, won't do anything because we have a lot of open to-dos left. This will just be to show you the basic process. Later on, we will download my own script that are already prepared. So you don't have to deal with all the technical details that are basically the same for other games. Let's download the script and place it beside the game folder. Then go to the My AI controller in the Godot project. Go to the sync node, select the training mode, or press the reset button and start the game. This should give you an error. Perfect. The error says assertion failed. The getOps method is not implemented, which is basically those lines. So we need to replace or comment out all of them. Here we need a pass because an empty function will also raise an error. Now the error should be gone. But the game will not start anymore because whenever we are in the training mode, we also need to start the Python script since Godot is waiting for the connection. I kind of crushed my potato PC, but it's no problem. To start the Python script, we go to the terminal. So you probably have it here. And we can clean all these messages. Before we continue, there's of course a very important step that we need to do, which is just to activate the environment. Then we need to go into the folder where we placed the Python script. And just copy that, type in cd, and hit enter. Then all you need to do is to type in Python lineal example.py and hit enter again. This should pop up a message that says waiting for the Godot. So we go to our Godot project. And hit play. Which will already give us our first error. It's something with the AI eyes, so to say. So in the upcoming modules, we will implement all these functions and the errors will go away, hopefully. Here is the error from last time again. And normally the last paragraph is what you want to look at first. That just says runtime error, cannot reshape tensor of 0 elements, and then blah blah blah. And if we look then more closely into the details of the error, we see observation space size 0. So this is where the problem lives. If we then go to the My AI controller, we can look at those functions, and this seems to be about the observation space. And actually, it's returning a dictionary with a list that has 0 elements in it. So what we do is just add some elements into it. This is of course just a temporary fix. But now we should be able to start the training. And by the way, if you restarted the terminal, don't forget to activate the environment and let the console know that we are in this path with the cd command. Anyway, to start the training, we just can press the upper arrow key until we find our command. If you have Clink installed, what you could also do is press F7. Then there's kind of a list. You can navigate with the arrow keys. Which messes up the border a bit. Then we start the Godot game. And now we see that the error is gone. And of course, our agent does not move because it still depends on the player inputs. So when I press the keys, it's moving and shooting and so on. But the connection between Python and Godot works now. By the way, if we look at our project folder, we see that beside our Python script, there was a log folder created. This just contains data for tracking the training, but you can delete it since this only was for a test run. In the next module, we will prepare our random agent. This is important because in machine learning, you need a baseline to compare your trained models to. For example, if an agent that chooses his actions randomly achieves an average game score of 500 points, then an agent that actually learns something should achieve a better score than this. Anyway, our next to do is to clean up the imgui code, because later on we will recreate it in the MyAI controller, since we are interested in debugging the agent actions, not the human player input. Let's go to the player GD. If it's not there anymore, you could also write it on the down left to find it. And in player GD, we search for our imgui code and can cut it out. Save it, and then we go back to the MyAI controller. And at the top, we can insert it. We can also delete all of this and take care of it later. We can also write the process function, func underscore process delta. And if you want to avoid these highlightations, you can just write an underscore before the delta. However, for now, we don't need this, so we can comment it out and go back to it once we have the random agent. Let's create the random agent. As mentioned in the last module, a random agent gives you a baseline to confirm the trained agent is actually learning, not just getting lucky. We need to define the action the agent can take. This of course depends on your game, but in Space Invaders it's just move left, right, or don't move. And of course fire. So at the top of the MyAI controller, we can just define two new variables. For move, this will be an integer. And for fire, which will also be an integer. we need to define these actions here in this script because the agent will send them to the game. So you can think of the MyAI controller as the communication script between Python and your Godot game. Anyway, let's go to the set action function at the bottom. And we can actually delete the assert line and the pass. If we will not use the random agent, which will come later on, not random agent, then we just pass for now. And otherwise, we let the random agent decide what action to take. I think it's best if I just write these 7 lines of code and then explain what is going on if you see everything. Variable random action equals rand integer range 0 to 3. This picks a number 0, 1, 2, 4, 3. Then if random action equals 3, we set move 1 and fire also to 1. Then let me write some comment. 0 equals left, 1 equals stay or don't move, 2 equals right. And for the fire, 0 equals peace or don't shoot, and 1 equals fire. Else, move equals random action, and fire equals 0. You can of course design this however you see fit, and it will be different for different games. But I find this to be rather simple once you understand it. And the Python scripts for the PPO and the PTR algorithm expect this structure, which you can of course also change easily. Anyway, what this does is that this random function generates a number between 0, 1, 2, or 3. And for example, if the number is not 3, it will not be in this branch. So the move will be 0, 1, or 2, which is move left, stay, or move right. And we set the fire to 0, which basically means don't shoot. So in the case that we pick the number 0, 1, or 2, it will just land here and define the move. And also here. And in the other case, when we pick the number 3, which all have an equal chance, so 25% in this case, we land in this branch, and then we set the move to 1, which is just stay, and we set fire to 1, which just means fire. So I did it on purpose that the agent can't move while firing, even though the game allows it. This is because if there are less actions, it's easier for the agent to learn stuff. And I think moving while shooting is not necessary in Space Invaders. However, I think standing still while not shooting is important, so I included this option. So standing still while not shooting, for example, the 1. If this gives us a 1. I think you will understand it. And what I mean by shooting while moving is quickly start the game. Human, great. Oh, we need to declare this variable. Let's go to the top. And define it properly. So if I move to the left and press shoot, we can shoot. The agent will not be able to do this. So if he wants to shoot, he would have to stand still, shoot, and then move again. You may be wondering why we don't return anything from set action. This is because of how we use the AI controller in our setup. It will be easier to explain the reasoning later, but it has something to do with frames per second, FPS. This analogy will hopefully help before we go into more details. You probably know that a movie is just a bunch of images that are prepared in advance and then shown to you in high speed. Games work similarly. A game is just a bunch of images that are drawn on the fly, which, by the way, is why you need a GPU for beautiful games. This means if the game runs at 60 FPS, then it's drawing 60 images per second. It will therefore execute the whole main scene and its code with 60 FPS. But there is a problem. The AI agent runs on a neural network, and we don't want to execute this with 60 FPS. We could do it depending on the hardware and the game. However, this would waste performance. Instead, we execute the AI code only every 4 frames, for example. And then the game grabs the agent actions from the myAI controller variables. In simple terms, on every frame, the game itself asks for a player or AI agent input or actions. But the AI agent only changes its mind after, for example, every 4 frames. That's why we store the current decision of the agent in the variable and let the game grab it. All of this means the agent chooses an action and it will be repeated for 4 frames until the agent chooses a new action. You can set the action repeat variable in the sync node on the right. Let's actually set it to 4. The optimal value depends on the reaction time needed, but also a bit on your hardware. I would generally recommend 4. Notice if a model is trained on, for example, action repeat equals 4, its performance will suffer if the value is changed. Anyway, if we press Ctrl, Shift and F and type in action repeat, then we see all of the usages in the whole project of this variable. If we look at the usage in line 189 in the sync node, then we see how it is used by the plugin. It is just skipping most of its code when the action repeat value does not allow it. So training, inference, and so on. If all of this is a little complicated, then don't worry, you don't need to fully understand it. It is handled in the background. This was just to give you a hint on how the sync node works. So if you're debugging anything, you know that on every 4th frame, this sync node stuff is executed, and on all other frames, it is not even executed. Anyway, let's close that. And in the next module, we will actually go to the player and shooting script and let the random agent control it. Let's give the random agent control about the player by grabbing the actions from the MyAI controller. For that, we go to the player script. And the first thing we need to do is to import our AI controller, so we can always access its variables. So at the top, we can write on ready variable AI underscore C. Node, it's a node 2D. By the way, this type hinting is not necessary in Godot, although it can increase performance a bit. And it's easier to read, so I always do it. Anyway, then we grab from the AI main scene, we grab the node by get node AI controller 2D. And that's it. Now we could do something like print AI controller dot fire, for example, and this would print our fire variable if the AI controller is active. I mean, it is active, but it's only an integer, and if we are in the human mode, it's not setting it to something. But if we're in the training mode, we'll access it from here. Instead of talking about it, we can just quickly test it, but write another print to know what's going on. Then we see it's always printing the same, even though we press fire. Anyway, we can delete those two lines and then make sure our random agent is controlling the player. If you want, you can pause the video now and try it yourself, but don't forget to set the sync node to training mode and start the Python script. Otherwise, the controller script that contains the agent won't be executed. Actually, I made a little mistake when importing the AI controller. If you look at the type of the node in the AI main scene, we see that it's just a normal node, not a node 2D. So we can delete the 2D. Anyway, at the top, we imported our AI main scene. This is possible because we set our AI main scene as an autoload. In project settings, globals, and here is its name AI main, autoload enabled. And then the AI controller 2D, just a node of this scene. Maybe I should have mentioned that it would be better to not just override the possibility for human input with the agent controls. The goal would be that when we are in the human mode, a human can still control the game. And when we are in the training mode, then the agent is controlling the game. Having the possibility to switch easily will make our lives simpler in the upcoming modules. The way we can do this is by making use of the control mode variable in the sync node. This variable is also accessible from our controller. Because it's inheriting from the sync node. So the control mode is inherited from the sync node. Enough talking, let's go down to the process function. Let's first look at the actual variable. Print AI controller dot control mode. So now we are in human mode, and when we print this variable, we see that it's just a 1. And when we are in the training mode, maybe I can print it without starting the Python. Nope. Then it's always printing a 2. We could just use an if-else, but I will use a match statement. It's minimally faster overall, and I just like it more. For that, we go to the top again and type in a new variable, so all of this is less confusing. Variable control mode. It's just a dictionary that maps the numbers to the mode name. This is not strictly necessary. However, it's good to have it in a clear manner. And 2 was training mode. Then we can just use this mapping in the process function. First, we can delete all of that until the delta movement. Actually, we need first line. Then we can write match and use our control mode mapping that we just defined above, which is a dictionary that receives a key. And for example, if we give it the key 1, then we get back human. So if I do this, then it's returning the string human. So what we do is we grab the AI controller and grab the control mode. And depending on what is set there, it will return a 1, 0, or 2. By the way, if you wonder what ONX inference is, this is just for inference. So when we have a trained model, we can use it without Python in the exported game. So for example, if you want to publish a game and you want to have a neural network in there, you would transfer the model into an ONX format, and then you would be able to use it. But this is an advanced thing that will probably be covered in a future course. In the case, the match results in a human string. We define a new variable called input, similarly as we had before, and then do input, get axis, move left, and move right. This is just from the input map, or will be from the input map. Then if input is bigger than 0, we say direction equals vector 2 and right. Then elif input is smaller than 0, we set the direction to left. And otherwise, we set the direction to just a vector 2 with 0, 0 in it. So if we go to human mode, this should still work. Perfect, I can still control the player. Then, in the more interesting case, training mode, we set the input variable to a controller.move. So we grab the current action that is set by the AI controller. And then we have another match, the input. If it's 0, we set the direction to vector 2 and left. Then also to 0 and to right. This is in the case 2, this is in the case 1. And then the random agent or array agent should be able to control the game. To test this, we can go to the controller script, because we of course need to set the random agent to true. So in the set action, it will actually use this stuff. And then you can go to the console. Don't forget to activate the environment and go into the correct path. And then we can just type in Python cleanerlexample.py, hit enter, and also hit the play button. So this looks good. And the agent is moving. It is of course moving randomly, but it works. If you tried to do this by yourself, don't be discouraged if it turned out to be a little tricky. I think this was one of the harder exercises. Anyway, if you want, you can try to do the thing we just did in a player script in the shooting script. This should be way easier now. The first thing we can do is to import our AI controller. For that, I will just copy these 2 lines from the player script and insert them on the top of the shooting script. The AI controller import and the control mode always look the same. By the way, I forgot to clean the imgui from here, but let's just leave it there until the random agent works. Then what I would do is to write a match statement. Again, with the control mode mapping, AI controller, grab the actual number from there, which comes from here. And then we are either in the training mode or in the human mode. In the training mode, we just grab our decision from the AI, from the fire variable. And we can actually transform it into a Boolean. This may be preventing some errors. Oh, and of course we need to define a variable in that case. In the human case, we also define a variable, but it will get the input from the player. Of course, we need to define this variable at the top. So variable should and false. Then we can also delete the player input from here and use our new variable. Awesome, this should work now. All right, let's test this. We can start the game and then open our console. Type in cd, open the path, and then activate the environment and start the Python script. So the agent was shooting already. Here is it shooting again and again. But if we observe it for longer, you may notice that something is off. Because in the beginning of starting the game, I clicked with the mouse and pressed some inputs into my keyboard, but when I don't do this, it's not shooting. When I first coded this, it took me quite a while to find this out. But if you look into the AI controller, scroll down to the set action function, then we can look at the random agent, the random function. So what it does, it gives an equal chance to each action to be created. So 25% for each of the actions. Left, stay, right, and fire. However, when we observe the game, this distribution was not observable, so to say. This is because we forgot, or I forgot, to change the input function. Because the way this function works is that it's only triggered when there is an input event. And then this whole function here is executed, but we want it to be always executed because when the agent is in control, we don't want to press any inputs. So there is an easy fix to that. We just delete this line and everything here is in the process function. If you did not press any keys and the agent was still shooting, it could be that the mouse movement is also counted as an input event. Because if you have a shooter or something, you of course control it with the mouse. Anyway, let's test it again. And I was using the arrow key now to quickly get the command. Great, now it's shooting all the time. and it's also moving all the time. So this seems to be as it should. And I think the imgui is not up to date here. So the shooting not pressed, we could change it, but we will delete it anyway now and move it onto the my AI controller. The agent now is pretty good, even though it's just random, but that's only one in, I don't know, 10 or 20 games. We can now move the imgui to the AI controller. So we visualize the agent actions instead of the player actions. First, I would delete it from the shooting script. So just delete all of that. And then save it. Then we can go to our AI controller. And decomment the process function as well as the imgui function. So every time the AI controller script is executed, we also execute the imgui, which then does what it does. So we will now just grab the move and fire variables and print them accordingly. I believe we can delete the inputs from the activate imgui function and just insert a bunch of space in here. If move equals 0, I think, set the action name to move left. Let's quickly check if this is right. Awesome, seems good to me. Then just copy that. Elif move to the right equals 2. And in any other case, we say don't move. Let's quickly test if this worked. But if you want, you can go to the sync node and on the right, decrease the speed up to about 0.2 or so, because if the agent switches up the actions fast, it's a bit hard to read. Let's start the project. It should be pretty slow now, but it's moving to the left, and it says move left and right if it's moving to the right. Awesome. Then we can do the same for shooting pressed. Let's define a new variable, call it shooting pressed. If fire is equal to 1, which is equal to true, so we can just write if fire. We set shooting pressed equals to shooting pressed. And in the other case, we set it to not pressed. This should also work now. No, it shouldn't. We should also print it, of course. Awesome. What we also could do is to visualize whether the agent is allowed to shoot. So you see if a bullet is in the air, the agent is still pressing, and maybe it would be nice to know if the trained agent realizes how not to press the button when the shoot is in the air, the bullet is in the air. However, for this to work, we need to go back to our shooting script. And in there, you already see the can shoot variable. This is the thing that tells us whether we're allowed to shoot or not. Because whenever the laser gets destroyed, it sets can shoot to true again. And if it's not true, we cannot shoot. What we need to do is actually pretty easy. We just send the can shoot variable to the AI controller. So we go AI controller and access its can shoot variable, which we have to define, of course, and override it with the can shoot variable from here. This is the only information we need. So in the my AI controller at the top, we can define a new variable, can shoot, and let's set it to true at the start. Then we go down to our imgui function, define a new variable, shooting allowed, set it to not allowed shoot, or to be consistent with the above, set it to allowed to shoot, because we started true. And then if can shoot, we say shooting allowed equals allowed to shoot. And otherwise, we are not allowed to shoot. Then we also print this variable. And this should be it. Okay, there is a little mistake. It's saying shooting not pressed 2 times. I, of course, forgot to change the variable name. Shooting pressed by shooting pressed and shooting allowed by shooting allowed. Awesome. I think this is looking good. He's allowed to shoot, and shooting is not pressed. Now he's not allowed to shoot because a bullet is in the air. Perfect. This will now give us everything we need to visualize our agent properly in terms of his actions. In this module, we will quickly cover weights and biases. It's a popular tool in data science that's used to track, manage, and visualize the training of AI models. Tracking can make the difference between aimlessly messing around and actually understanding what's going on. That's why I will now explain weights and bias a bit, and after that, we briefly talk about our PPO Python script, so we can then create the actual random agent graph. I think the easiest way to explain our goal with weights and biases is to just show you the finished visualization. Each agent we train will generate 3 different graphs. This is the first one. It's created by the random agent. Let me quickly zoom in a little bit. Awesome. To explain this graph a little bit, if we look at the x-axis, you see it says step. A step is one exchange between the agent and the game. So the game sends an image and reward, and the agent sends back an action. For example, on this chart, we have 18 million steps, which represents about 9 hours in this specific case, because it was done with 6 environments in parallel and a game time speed up of 10x. If we look on the y-axis, we see the in-game score. By the way, in our Space Invaders game, the max high score is 1100. So to be more precise, this is the moving average game score. For example, if we look at the step at 2 million and see a game score of about 400, then this 400 represents the average of the last 200 games. And if we look at the step at 6.3 million, so at this peak over here, we see that the last 200 games up until to this point had an average game score of about 425. This graph is called moving average game score because the window of 200 games keeps sliding forward as the training continues. And by the way, if we hover over the graph, I quickly take a screenshot so I can control this thing. If we hover over the graph, we see this box here. So this 6.3 million is the step value, and from the x-axis, and this 423.05 is the game score. And then we have an ID for this specific training run. We use a moving average for all of our graphs because a single game score just jumps around a lot. One game, the agent gets lucky, the next one, it doesn't. Without averaging, the graph would just look like noise, very chaotic and hard to read. The moving average smooths that out, so we can actually see the agent's tendency and understand if he is improving or not. Back to the random agent. I ran him for about 9 hours, so you don't have to. I think the tendency of the chart is clear after about 1 or 2 hours. What I mean by tendency is that the random agent tends to produce an average game score of about 400. Of course, it fluctuates a bit, but this gives us a clear goal which we can trust, namely to clearly beat a score of 400. The peak of this 9-hour run, or 17,000 games, is 425, about here. So I think if we can produce an agent that scores 450, average on 200 games, then we could say the agent already learned something. Which would of course only be a minimal confirmation of success, but this is kind of the thinking around this. Anyway, if we actually look at the real first PPO agent, we see that we were indeed able to beat this baseline. I trained the agent for way longer than the about 13 hours you see here, but more on that later. The important thing to notice here is that we already reached a score of 450 after about 1 or 2 hours of training. So even with the very low parallel environment count of 6, it would only take 2 hours to confirm that our AI agent is actually learning something. The important thing to remember here is that if I had a proper reset function in the game or better hardware, we could easily speed things up a lot. But because it's simple and more accessible, I trained the PPO agent this way. Actually, let's just look how the graph is evolving. So after 40 million steps, we see that the performance declined, which is of course not good. But if we look then to 70 million steps, we see it was actually just a local minima, so to say. And we found it 50. From 450, we actually reached 600. Then if we look even more at 120 million, we see that we also beat this 600, but only by a tiny bit. If we then jump to, let's say, 140 million, we see that we achieved a new high score of 750, which is pretty nice. However, if we look at the full graph, we see that in the end, our agent achieved a score of 900, which is good, but not perfect, of course. Since the score for shooting all aliens is 1100. Let's quickly talk about the two other graphs. On the left, we have the moving average reward. It's pretty similar to the game score graph. The only difference is that it's showing the reward instead of the game score. Because we're mainly doing reward shaping in this course, every agent will have a different reward graph. Because of this, we cannot really compare the reward graphs of our agents. But the game score works the same for every agent, so we can compare them. On the right, we see the moving average win-loss ratio. The win-loss ratio part is easily explained. If we play 200 games and win every game, then the ratio is 1, or 100%. If we lose 100 games and win 100 games, then the ratio is 0.5 or 50%. And if we lose 200 games, you know the ratio. It's 0. I just realized that the name of the chart is missing the word average, so don't be confused. The moving average part of this graph works the same as for the other graphs. Anyway, the thing we can reach from this chart is that PPO agent 1 only achieved a win-loss ratio of about 6%. If the agent wins 6% of its games, then if it's playing 200 games, it only wins 12 games. With that, I just spoiled the first agent. but the other ones will of course perform better. Before we move on with the coding, let's quickly talk about the navigation on weights and biases. If you created a free account, you will see this overview page, where you see your projects and your runs. Let's click on projects. Normally, I would create a different project for different games. And clicking on a project brings us to the workspace section. Here you see the graphs we already talked about. And the PPO Python script also produces some more technical graphs, but you don't need to look at them, since dealing with losses is kind of an advanced thing. And there are also some system graphs. You can also ignore those. But for example, if we go to the next tab, the GPU temperature graph could be interesting. You can actually see that the random agent was way hotter because it had like 30 degrees in my room when I trained it. So this is the random agent, and this was the first PPO agent that was trained before the summer. On the left, you also see more options, but only the workspace and the run sections are important. Let's click on the runs. Here you see a lot of details about each run, and you can actually scroll to the right to see the hyperparameters like the learning rate or other stuff. You can also type in notes for each of your run, and for example, look at the runtime. So the random agent was ran for about 8 hours, and the last PTR agent for a day and 1 hour. The way I prepared the pipeline, it makes it really easy to provide custom information to weights and biases for each run. So for example, I provided this dictionary and I could write in whatever I wanted here, but I decided to provide it with the random word, which just says it's a random agent. Here I said PPO agent 2. And I also have the action repeat value that controls the reaction time of the agent. But we will talk more about the reward structure and so on in later modules. If we go back to the workspace section, there's a nice little thing about weights and biases. You can always toggle the visibility of your graphs. So if you want, for example, to turn off the PPO graph, you can just close the eye. And then we only see the chart of the random agent. If we turn it back on, it's back on. We can also open individual runs by clicking on them. And for example, look at the command, logs, and files that produced the run. In the overview, you also see the command that started this training, where you can see that I use a parallel environment count of 6. We will talk later more about the parallel count. Anyway, overall, if reproducibility is important to you, then weights and biases is a pretty nice tool. But I think your Godot game code is only properly trackable if you upload it to GitHub. So keep that in mind. Don't forget, if you need a recap of weights and biases, you can read the most important parts in the description of its module. Anyway, in this module, we will have the first look in the Python PPO script that I already prepared. I designed the script so that you can use it in a plug-and-play manner. I did this because I think talking about it in too much detail would explode the scope of this course. Since it has like 600 lines of code, which is the case because the full PPO algorithm is in this script. Big scripts are a disadvantage of clean.rl, but also an advantage, because you can look at the full AI code the algorithms are made of. For example, we can look at the agent and see how the neural network is built. In the case of PPO, it's really simple. It's just a convolutional neural network in order to be able to handle images. The BTR algorithm will also cover a CNN network. However, there will be way more complexity around it. Anyway, we also need to download the script. So you can open the link in the description to this GitHub repository and click on click on PPO11 and on the download button. Then you can move it in our folder besides the Space Invader game. And if you're wondering about this folder, the Git folder, you can ignore it, you don't need it. This is just because I uploaded everything to GitHub, so I have a backup. If we open the script, and you can open it in any editor you like. For this course I chose the Notepad, but sometimes I'm also using PyCharm or VS Code. If you can remember, we had this information about the rewards on weights and biases. We will take care of it in Godot now, before we then create the graph for the random agent. We are back in the MyAI controller of the Godot project. And we can define our reward structure at the top of the script, so we have a central point of controlling our rewards. So on ready, we define a new variable. Let's just call it rewards. And it will be a dictionary. So normally you don't write this AND operator in dictionaries, but I use it because it just says this key won't change and gives a tiny bit of performance. It's probably neglectable, but if we have the possibility, we can do so. Anyway, the first agent we're taking care of now is just the random agent, so we call it random. But we can already define the reward keys. So we have game lost, we also have life lost, and game won. And finally, alien shot. There will be more rewards later on, but for now, those are the ones the first agent will have. And let's set all rewards to 0 for now, since the random agent doesn't care about them anyway. And before I forget, let's also leave a comment here about the action repeat value. Since it is set in the ready function, which we need to define afterwards. This is because the action repeat value can be set in the sync node, and if we set it in the editor, Godot has no possibility, or only with workarounds, that we read it here from the editor. So we will have the ready function, and this will read it into the rewards dictionary. And to be precise, it is of course no reward, but since it is bound to the model, I thought it was just simpler to have it in this dictionary. And therefore in one place. Awesome. Awesome. Let's take care of the ready function. I would write it above the process function, because this is also the order the functions are executed. So ready returns a void. Then what is also really important, if we define the ready function in the Maya controller, what happens then is that since this inherits from the original AI controller script, let me open it quickly. What happens is that we override this ready function, but this add to group is really important because it connects the sync node with the AI controller script. So what we do is we just write the super argument or command super._ready. Now, when we call our super function in my AI controller, our ready function in my AI controller, it activates first the super function, which just says, hey, go to the original AI controller and execute this line. Then we can set the action repeat value in the rewards dictionary. So we grab the dictionary, and create a new key called action repeat. And in it, we just do get parent, because the parent of the AI controller is the node. And then we say get node sync. This is just the name of the sync node. And from the sync node, we want the action repeat value, which is then just this thing here. So to confirm this works, let's just write a print statement. What's agreement? And this print statement is also nice because now, whenever we start the training, we will print our reward structure. So this is just to prevent the case where we expect one agent to train, but have a wrong value here. So the command line will show us this dictionary again. So the chance of we doing something wrong decreases a tiny bit. So in this print statement, we just do JSON. Since the dictionary is just a JSON, there is some functionality behind the JSON call, and we give this stringify function our rewards dictionary. And the indent string is just 3 spaces, so it looks a bit better. And we don't want to sort the keys, so we provide the false argument. Awesome. This should already work without the training mode, because I think the ready function is executed whenever we start the game, but the process function or so is only executed once. Okay, if we look into the prints, we see rewards in this experiment, agent random, action repeat 4. Awesome, that worked. What we can also do is to do another safety thing, namely if random agent. So if this is set to true, then we print a warning. Warning using the random agent, which means the AI will not learn anything. Which should work now. Perfect. So we always see the reward structure that we currently have and a little warning if the random agent is active. Now we want to send the reward dictionary to Python. So Python can send it then to weights and biases. For that, we will just include the info dictionary in the packages that we regularly send to Python. So in the ... so to say. If we open our PPO script again and search for experiment rewards, then we see an empty variable on line 322, and on the next usage is here around line 400. So what happens that the slide you were just shown before shows this process. So an environment step or exchange gives us the infos, and it gives us the rewards, and it gives us the screenshots or images or raw observations. It is also giving us the terminated and truncated information, which is just if the episode has ended. An episode is if the game has ended. So if the agent loses all of his lives, then the game has ended and restarts, and this is an episode. So basically what this function does is that it takes the Godot environments or the Godot games and says execute one step. So this is where the Godot then sends the information to Python, and from the environments then we get the information, so to say. And this reward dictionary is just in the infos. So what we do is, if the tracking is available, the track is just the command that controls whether we use weights and biases or not. We will talk more about the commands later. But if you want to get the information and the experiment rewards are not there yet, because it is makes only sense to send them once or to receive them once, then we just grab from the infos dictionary the experiment rewards, and then we send it to weights and biases. In the controller, we can define a new variable on ready variable info dict for Python. And we just create a dictionary, type in experiment rewards, and provide it with our rewards dictionary. Then in the bottom of the script, we can use another function that is provided by the AI controller. Get info, and there we just return the information dictionary. Awesome. Before we can test this, we need to connect our terminal to weights and biases, which should only take 1 minute. So the first thing is to activate the environment if you don't already have. And then you probably need to install weights and biases. I think I already installed it, but just type in pip install weights and biases. Installment should be pretty quick. If you are able to spell it correctly. Then we can clean the commands, and then we can go to the page of weights and biases. If you haven't already created a free account, you should do it now. And if you have an account, you can log in. And then on the upper right, you can click on your profile picture and select API keys. You should have no key there, but I will also create a new key. You can name it however you want. Let's just call it Space Invaders key. And it's not a big drama. If you lose the key, you can just create a new one and reconnect in your terminal. And probably I won't use this key and I will delete it because you saw it. Anyway, let's copy this key. Press done. And in the terminal, make sure you are in the right path. And then we can do Python and press the tabulator until we get the script suggested. Press enter. We will talk about this stuff later. For now, let's look at the weights and biases things here. We use an existing account. So we type in 2, hit enter, and then we type in our key. You don't see it because the terminal just don't show it. Okay, you just have to make sure that you insert it exactly once. So press one right click, because right click can also insert stuff, or one Control V and then enter. And yeah, maybe you have to try it sometimes. Anyway, we can then start the Godot training. And we get an error because of the observation space, but I think the rest worked. So the connection to weights and biases should be good now. And I will delete this key from my account. Anyway, if we go to the biases page now and select the project, currently you have it in the test Space Invader. We can see under runs our runs. However, the reward dictionary is not there because the AI controller is missing some functions. The end of the last module was a bit messy, so we need to fix the remaining things now. The Godot AI Agents plugin expects us to use all of its functions that are implemented in the template. If you can remember, we downloaded the template before. So it's the get observation, reward, and action space, and set action function. Let's start with a quick temporary fix for the agent eyes. Above the ready function, we can do the following. Just define another onReady. This is a variable, we call it 0 observation. And it's a dictionary. So we provide the observation key, just as it is in the get observation function. And then we just type in this stuff. 84 times 84 times 2 with a bunch of zeros. This will just send a black image to Python. It comes as a string because the network of the plugin works best if it's sending strings. In the Python scripts, there are already functions that transform the string back to a proper image. But don't worry too much about this, because we will talk more about this in the Agent Eye module. For now, we just go to get observations and return our black image. So just copy that and paste it here. So whenever Python asks for a screenshot of the game, we will now send it this 0 observation. We can also delete this assertion line or comment. Then we can take care of the get observation space function, which was not even defined in the controller, but we still need it. Let's just write it and then explain it. So function get observation space to be continuous with the writing. This will get also a type hint because it could return a dictionary. But if you don't like the type hints, you don't need to do them. Anyway, then this returns dictionary with the first key being observations. And then we have another dictionary. the size key, and the space key. So the size is 1 times 84 times 84, which just stands for channels, height, and width of the image. And the space is just a box. Here we just tell Python the size and shape of the observation, or the shape of the vector we are sending if we don't send images. So we only send a resolution of 84 by 84, because otherwise the AI has to deal with way too much data, and the training would take much longer. I think the Mario Kart AI that I talked about earlier only worked with images of the size 84 times 120. So this small size should work for most games, since Mario Kart is a complex 3D game. Then we can go to the action space function. Depending on your environment, this could be a little complicated. However, in Space Invaders it's easy, since we just have decided to use 4 simple actions. So first, get rid of this comment here, and actually all of that. So we return a dictionary again with the action key that contains another dictionary that has the key size and action type. The size is just 4 because we define it like that, and our random agent also shows it. Then the action type is discrete. The important thing here is that if you use a different number of actions, don't forget to type in the right number. By the way, if you had continuous actions, because for example you're playing a racing game with a controller, I would recommend using the discrete actions anyway, and just splitting it a bit. So for example, you could do 100% right, 50% right, and 10% right. So you had 3 actions for the right movement instead of 1. This way the AI still has precise control, but you don't have to overwhelm it with the infinite options a controller provides. Awesome, that should be it. Let's test things. I forgot to increase the speed again to 1. That's why it's in slow motion. But you can actually watch the PPO agent decide in real time. So I'm not pressing any keys. And you see the inputs here. Of course, this is an untrained agent, so it's more or less random. And if you look into the terminal, we see experiment rewards, but not the dictionary. That's not good. And yeah. You can also look at this prints. This is still showing this stuff from before. Great. Let's interrupt this thing and turn the speed back to 1. In our PPO script, I inserted the print for the experiment rewards. So if we start the training now, we should be able to also see them in the console. Awesome. And what's also important is to look at the weights and biases page in the test Space Invader or however your project is called. You can go to runs, and then there should be this thing, which is the experiment rewards. If it's a bit annoying to find it in here, you can go to the columns button and first of all search for it here. And then you should find it on the left or the right and drag and drop it to the right. And yeah, then you can also drag and drop it here to the top if that's easier. By the way, if you want to change the project name that is shown in weights and biases, you can go to the Python script, type in project name, and then change the default name. Currently, we send the rewards dictionary continuously through the whole training, which is not a real problem since it's basically size 0. But to be clean, we only want to send it once. However, because of a tricky thing in the way the Godot AI Agents plugin starts and connects with Python, sending the information dict only once and then deleting it does not work. The easiest fix I found for this is to just send the reward dict 10 times and then delete it. Normally in networking, you would send it until the receiver confirms it got it. But implementing that would be a little too much. So we just hope the receiver received it, which does work pretty nicely. So the first thing we can do is to define a new variable at the top below our info dictionary. Info send counter, and this is an integer with the number 0. Then in the getInfo function, we just write some simple logic to deal with this. If info send counter is bigger than 11, we just pass. Elif info send counter equals 10. We say info dict for Python and then erase a dict from it, a key from it, namely the experiment rewards. Then we set the info counter to 11. And in the case it's not bigger than 11 or 11, we of course have to increase it by 1. What this does is pretty simple. Every time we send a package to Python, we also increase the info set counter. And in the case it reached 10, we erase the experiment rewards from the info dict and set the counter to 11, which is where it will stay for the rest of the training. That just means if it's bigger than 11, we don't send the information. We don't do anything anymore. Later on, this information dict will contain more information, but that's not relevant for now. Now we don't have much to-dos left, or we can start our first training run with the random agent. But independently of the reasons for the baseline we talked about earlier, this is a good opportunity to figure out if everything works properly on your system and how much it can handle. In order to train multiple agents in parallel, we will now export the game. Exporting the game means we get a normal program that we could start like any other program. In Godot, this is pretty simple. You just go to the top left, click on Editor and manage export templates. Then you should see this warning, export templates are missing. We just click download and install, which is the easiest option because it automatically downloads the correct version. In my case, that's Godot 4.6.1. I also had other versions from previous setups, but 4.6 is the current one I'm using. This could take a while because it's 1 gigabyte, so I will pause the video now. Awesome, it says export templates are installed and ready to be used. As a side note, you don't need to repeat this for other projects. Every project that uses this specific version of Godot will use the template you just downloaded. Now we are ready to export our project. But before that, I would also increase the training speed up in the sync node to 10x. So we get the maximum number of frames. Then you can go to Project, Export, and select a preset. I will use Windows because I'm on Windows, but Linux and macOS could also work. I have not tested this myself, but the plugin says so. Let me make it bigger. What I would do here is to set the export console wrapper to no and the embed PCK to on. Otherwise, we will export more files than one. Then you can go to Export Project and export it with debug and name it however you want. I named it Space Invaders. If you already have exported it, just override it. For you, if this is your first export, this maybe will take 10 seconds or so, but for me it was a bit faster. You should then see the executable in your project folder. And what you can do then is to copy the path. Because now we will open the console, go to the path, activate the environment, clean everything, and then start the training. So we can type in Python, the name of the script, then provide the environment path, Just insert it, and then you write the name of the executable. In my case, it's Space Invaders .x. Then you provide the number of parallel environments. Let's first try it with 6. And last but not least, we provide track equals false, so we don't send any data to weights and biases, because this is not needed for now. Then if we hit enter, there will be a lot of stuff. What Godot is doing, it is opening 6 of the instances in parallel, and every instance gets all of its prints shown in the terminal. So this is quite a lot, but we don't the end. And we maybe should disable this print that says "Lose a life." So on Windows, you can use the desktop view. Oh, I should press enter. Sometimes the console pauses when you click into it. Then in this case, you just press enter. And if the cursor blinks again, everything should move again. Okay, we see there are 6 instances of the game. Maybe let me restart it, because we have no automatic restart yet. Just press Ctrl+C. Then there are a bunch of errors you don't care about. And you can type CLS to clean everything. And use the arrow keys to get the command again. So once every window is open, the agent will start to control the game. Maybe we will later on disable imgui, but for now it's okay to see it. You could also move all the windows if you like, but it does not matter. Later on, we will also automatically let the game restart. But this is looking pretty good. The main thing here is that it's a bit tricky to figure out how many executables your PC is able to handle. For example, I can start the training with more than 6 environments, but my PC crashes after some time because of weird issues like memory leaks. So I think the Godot instances are fighting for memory. If you only have 16 gigabytes of RAM, then maybe you can only train with 6 environments. However, since the FPS count is about 500 for each instance, maybe we can see it somewhere. If you train for a bit longer, you will see the FPS count here in this section, because this will pop up regularly. But what I wanted to say is that since the FPS count is very high, even though my laptop crashes if I use more than 6 environments, it should be easily possible to have way more than 1 agent per 1 game executable. But as mentioned before, this requires a more complicated setup. Let's quickly disable the print statements we don't need. So go to the UI.gd. It was mentioned in the console, and then you can search for print. which is here, print debug, lives left, and comment it out. By the way, whenever you change something in Godot, you have to export the game again before you start the training. But that's pretty fast. It's like less than 10 seconds. And for developing, we started via the editor, so you don't need to export every time, all the time. Let's reset the speed up and the control mode to human mode. Currently, when we lose or win the game, we have to click on the restart button. I don't know about you, but if our AI plays 10,000 of games, then I don't want to restart them by hand. When I did all of this setup for the first time, the automatic game restart was actually one of the hardest parts for me. It took me a lot of learnings and trial and error to get it to be stable, and also to work without really touching the game code. That said, here's a quick recap of the parallel training options we do in this course. So option 1 is multiple instances of the exported game at once, each with only one agent. Option 2 is just one executable with multiple agents in it. And option 3 is a hybrid of 1 and 2. We use option 1. Since we want to use option 1, we need to do a little trick. This basically means we are using an AI main scene, instead of having a reset function in the game. But with this AI main scene trick, we can easily restart the game without having to reset every tiny thing that is going on in the game. A quick note before we start to code. If you are not interested in how the game restart works, you can just copy-paste the code we will write in the AI main GD and only code the relevant parts in the MyAI controller and the UI GD. Anyway, we need to manage our game restart outside of the original game. So we just use the AI main scene for that, because the original game is just in the main scene. And the AI main scene lives in the autoload. The first thing I would do is to go to the AI main scene tree and rename the first node to AI main. Then you can attach a script to it. This name is fine, so press create. First, let's talk a little bit about the game tree of the main game. So if we click on the main scene, we see the game tree that contains everything that the game has inside of it. This should be the same for other games too. So you have one big scene where your whole game lives. For example, if we start the game and click on the remote tab, then we see what is going on during the game. So the local tab, the local view is just a static game tree, and the remote tab is everything that is going on right now. For example, if I click on this, let's pause the game. For example, if I click on this thing, then this area 2D is this alien. So the goal of the automatic restart is to just grab the full AI main scene during the execution of the game or the training, and then to delete it and reload it again. And because of this reloading, everything is reset and we don't have to deal with the resets manually. That's the whole trick. If you wanted to, you could also print the scene tree. I just quickly use the ready and grab the current scene, and then the print tree pretty function. But you don't need to do that. So if you then press on play, we see the whole game tree printed out with everything inside. But we don't actually need that. So the first thing I would do is to test whether the restart and the reloading of the scene tree or game tree actually works. To quickly test this, we can use the input function, so we can trigger it automatically. If input is key pressed, let's use the arrow key, and then we can print a message. Restarting game. Restarting game because of arrow key press. And then we call our reload game function, which of course we have to write. As mentioned before, you don't have to understand all of that because it's basically the same for other simple games, maybe even for more complex games. So if you just want to play around with or practice reinforcement learning, then you can code along, and if you don't understand it, it's not that big of a deal. The first thing is to define a new variable. Let's call it old scene. And then get tree, grab the current scene. The current scene is the scene that Godot shows when you press the play button. So actually, if we go to the project settings and then under run, you see here that the main scene, or the thing that will become the current scene, is set to main scene PCN, which is just our main game scene that we want to restart. Then we can do a little check if we actually got the scene. If old scene dot view 3. What this is doing, control left mouse, is it's deleting the node and all of its children and all the references and so on. And it's not immediately deleting it, it's doing it in a smart way. Since a lot of things can happen during one frame, we will code another prevention, an error prevention. Await, get tree, and process frame. So what is happening now is that we delete the whole game scene, then we wait for the frame, and then we continue with the function. After the Space Invaders game scene is deleted, we need, of course, to load it again. So we define a new variable, scene resource, then load, and search for the main scene. There it is. Then we create another variable, new instance, So we can actually load the scene we just loaded into the memory into the game or into the game tree. Scene resource dot instantiate then the next thing would be to grab our new instance and change its name. Because if you have any references in the code to the main scene, then things can break. The following line will actually place the scene into the game root. So we do get tree, then root, then children, or add child, and insert our new instance. After that, we can call get tree again, then current scene, and this will be our new instance. So what this line is doing, basically doing the same as we would set it in the run here to be the main game scene. Awesome, with that, the game restart should work. So let's start the game and go in the remote tab. And then if you press the R button, we should see the game restarting. But maybe you have noticed something. So if you look at the bullets, they will stay there even though I reset the game. I give you a second to figure this out. But maybe you already saw it. So what we are doing is when we press the R button, we reset all of this main scene tree thing. But some of the areas are outside of. So for example, if we pause the game and click on the areas, we see that this bullet is outside of the main tree. We could actually go into the game and fix this, but there is a better and faster way to deal with it. What we will do about this is that we will have a function that is just resetting everything under the root and that has an exception list. So for example, the AI main scene won't be resetted and the imgui is also untouched. And if your game needs it, you could also put other stuff in the list, won't get reset. But all of these area things will get reset if you wanted them to. Let's make some space under the u3 command and then define another variable which allows us to grab the root node, get tree and root. Let's define the list of things we want to keep when we restart the game. The main scene, because this will be resetted already here, and the AI main, and the imgui root. Then it's pretty simple. We just loop through all of our childs and Q3 them. For child on root node, in root node. And get children. If not child name in our keep list, then we delete it. Awesome. Now the research should work properly. If we start the game and click on remote, minimize that. And if I then press the R button, then all bullets are disappearing. Great. So the next thing we want to do is to let our AI agent call this reset function. Now we give the AI controller control about the reload game function. For that, we go to the AI controller, and on the top, we can define a new variable. Let's call it restart game and set it to false. Then in the UI GD, we can import our AI controller. So let's do it here. On ready, variable AI controller. It's just a node. And we grab it from the AI main scene. So this is the same pattern that we had when we gave the controller control about the player. So we sent the information from the Space Invader game code and the main scene to the AI controller rather than the AI controller asking for the information. But that's why we define a variable here. So we can just use it outside of the AI controller. Back in the UI GD, we can search for every function that is responsible for a game restart. Because the UI is basically the UI that you see when you lose or win the game. So I think on game lost is relevant, on game won is relevant, and on restart button press is not strictly necessary, but I would also add it for more stability and cleanness. So what the restart button press is doing when we're pressing the restart button, it's basically reloading the whole scene, the whole tree. This is the light version of what we have coded in the reload game function. But we don't need it anymore since we will use the reload function in this case as well. So for that, we just grab our AI controller and send it the information, which is restart game equals to true. So later on, we will then code a function that handles this restart game correctly in the AI main. So when the controller receives this true signal, this signal to restart the game, so to say, then the controller will restart the game and will set the internal variable or its memory to false. So it will know I have restarted the game, it's false again, and it will be true again once the game wants it to be true again. A little side note, I called it signal, but this is not a true signal, because in Godot you have a mechanic that is called signals, which works a bit differently. So for example, when we look in the shooting script, we see laser tree exited and connect on laser destroyed. This is a proper Godot signal. And it's basically waiting for the signal to emit. And when it's emitting, then it sends can shot to true, which we talked about in an earlier module. Anyway, we can copy this and add it over here in the game 1 and also in the game lost. Awesome, that should be it regarding the UI. Let's go to the MyUI controller and into the process function. If restart game, we pass for now. But this restart game will be true whenever the UI says so. The most important thing that we need to have in mind now is that the restart function should be triggered exactly once. So if you would trigger these functions for several frames in a row, it would be very unnecessary and may even cause instabilities. So this code maybe will seem a bit more complicated than necessary, but this is all to avoid the problem of executing it for more than one frame. Let's go to the AI main script, and we don't need the ready function anymore. So we write the process function instead. And if you don't want any highlightation, because we don't use the delta, you can place an underscore before it. Okay, since we want to make the reset only once per frame, we will just count the frames, and this will help us a lot. Frames count per episode. By the way, in Space Invaders, one episode equals 3 lives, and an episode is just one game in general. So let's write a comment on that. And actually define the variable. Frames count per episode, and we start with 0. This function is, or this variable is also nice, because in reinforcement learning, we want to know when an episode has ended. So for example, we will send the game over information to PPO or to PTR, and it will use it to better train and learn. Then we can define a function to handle the game reload. Handle game reload. It will input the restart game variable or pseudo signal. So this is the one the AI controller uses. And then what we want to do is if restart game, we basically want to call our reload game function. So we don't need this anymore. As mentioned before, the Space Invader game sends the information to restart the game, or the pseudo signal. But the AI controller has to set this restart game variable back to false. So we will finish this function in a second. First, let me return the variable restart game. And then we go into the AI controller. Then what we do is to just write restart game, grab from the AI main, grab the handle game function, handle restart function, and plug in the variable. So the process function of every node is executed on every frame. This means when we receive the pseudo signal from the UI, we have the restart game is true, and then we send this variable to our AI main function, which handles the game restart, and this loop keeps going on. And if we don't receive a false pseudo signal from the game, then we will just send the restart game equals false, and the handle game reload will basically do nothing. Maybe we could have done everything that we did in the AI main script in the AI controller, but in order to have a better structure and separate things, I moved everything that handles the game restart in the AI main, and the AI controller is the bridge to Python. Okay, in the AI main script, we can just type in restart game and set it back to false. So to test this, we can quickly go to the live manager and decrease the lives to 1 temporarily. So it's faster. Awesome, the game was immediately reset. But actually you don't want to reset the game in the same frame the reset signal is received, because you want to finish all of the code of the current frame. That's why we will delay the actual reset a few frames. Overall, this just increases stability. Because with parallel training, networking, and screenshot taking, and so on, there's quite a lot going on. So the first thing we want to do is to catch when the restart is triggered. For that, we define a new variable at the top. Let's call it restart triggered at frame count, and we set it to -1. So when a restart is triggered, it has a positive value or 0, and otherwise it's just -1. I think I will first do the code and then explain it afterwards. So in the handle game reload function, we can type in another if statement. If restart triggered at frame count, smaller 0, we say restart triggered at frame count equals frame count per episode. Then the next if statement, if frames count per episode minus restarts triggered at frame count bigger equal 5, then we can actually do those two things and something else. Frames count per episode equals 0 and restart triggered at frame count set back to -1. Awesome. Maybe you already understood what is going on, but let's quickly explain it. So if the UI does not send us a restart signal, then this restart signal, which is false, gets sent into the AI main in the handle game reload. And the handle game reload just ignores it because it's false and then returns the false restart game signal. Then on the first frame, the UI sends us the restart game equals true. We receive it in the handle game reload. And since it's the first frame, our restart triggered at frame count is still equal to -1, which means it is smaller than 0. So we just catch the frames count per episode, which could be 100, it could be 200, it could be 0. And we override the restart triggered at frame count. So we save this number. Then, if frames count per episode minus restart triggered at frame count is not bigger than 5, which it isn't in the first frame, we don't do any of this. So we just return restart game false. Then in the next frame, and this is executed on every frame because it's in the process function in the AI controller. In the next frame, our restart triggered at frame count, where the name is quite long, sorry. It's not smaller than 0. It has the number we had, for example, 200. So this is ignored. And this is not 1 anymore. This is now 2. But it's still not bigger than 5. So we do this loop then again until this delta is bigger than 5, which it is after 5 frames. And if it is, we just set the episode count to 0, set the restart triggered at frame count to -1, and actually set the restart game to false and reload the game. So then the variable that is returned is false, but we actually restart the game. So let's test what we just did. And we can activate the remote view. So when we catch a bullet, the areas disappear and the whole game is reloaded. Awesome. As I mentioned before, you don't have to understand any of that, since it normally will just be the same for other games too. So PPO and PTR want to know when an episode has ended. In Space Invaders, one episode equals one game, which equals 3 lives. So therefore, we will now use the getDone function from the AI controller. Let me first write the code and then I will explain it. Let's go to the AI controller, and in the process function below the imgui activation, we can write a few things. So if restart game, which is the same variable that we get from here, and not that game previous, this will hold the reset game value of the previous frame, which means this is true for one frame only. Maybe I should have mentioned that the important thing now is, of course, that the game over or done signal for episode has ended information is only sent for exactly one frame, because otherwise the AI will kind of be confused, because the new episode will start and end immediately. Then we can do restart game underscore pending equals true, and outside the if statement write restart game previous equals start game. Awesome. Then we can of course define the new variables. I would do it below the restart game variable. So just copy this 2 times, and one time we add previous, and another time we add ending. Then above our getInfo function, by the way, you can also use this for quickly jumping functions, we define our getDone function. Function getDone, and the type hint will return a boolean. So if restart game pending, then we set restart game pending to false, and we return true. Otherwise, we just return false. By the way, if you're wondering what this window is, I'm pressing save all the time. It's just a habit of mine. Let's try to explain what is going on here. So, as I mentioned, the goal of this is that we send the information that the game or the episode has ended for exactly one frame. So in theory, we just could have used the reset game variable. However, I think I had some problems when I just did getDone return restart game. So something like this. Didn't really work because of the way the sync node calls the functions of the AI controller. So this is why we ensure that the getDone function can return true only exactly once, and then otherwise it returns false. And the way we're doing this is pretty simple. We just define a pending variable for exactly this reason. This pending variable is only set to true in the case that, or maybe let's play it differently. Let's assume we are in frame 1 and we don't have the restart game signal. then all of this is ignored. And then when we are in the next frame and we receive the restart game signal, what happens is that restart game is true and restart game previous is false. Then we set restart game pending to true. And after that, restart game previous is also set to true by the restart game variable. So what happens then is in the getDone function, restart game pending is true. So we set it to false and return true exactly once. And then back in the process function, if we are in the next frame, restart game is still true, but restart game previous is now also true. Which means we don't set the pending value again, and restart game previous just also becomes true. If you can remember, the UI sets the restart game signal to true, and then it stays true because for 5 frames, because in the AI main we told it to. Anyway, I hope all of that is not too confusing and that it was understandable. But this is the same as before. You don't have to really understand it because it will be the same for almost every other game. If you want to quickly test all of this, we can go to the sync node and deactivate the human mode so we get into the training mode, and then open our PPO script. By the way, since we don't have any proper training runs, you can delete the weights and biases folder. So if we open our PPO script, we can search for environments.step. So this will take us on around line 400. Where are these print statements? You can decomment them. So just delete the hashtags and make sure they are on the same level as the if statement of the args track. Then don't forget to save and start the training. So this time we don't need parallel environments because we will start it from the editor, and we provide track false because we don't care about weights and biases for debugging. Then in the Godot, press play. And now we should see the right information as soon as our agent loses his life. I hope this happens fast. Awesome. So end the game. And then somewhere here it should say false for exactly 1 time. So if you don't find it, you can also copy all of that and insert it somewhere. Maybe just make a new file, insert it, and then search for done. Or what was it? It was true. Then just search for bracket true. And so 1 line like that means 1 exchange with the Python environment between. So Godot sends the information of the reward, the done signal and other infos to Python. And so this is done a lot of times. And we see that the terminated and truncated, which is kind of the same thing, it comes from our getDone function, is true for exactly once. So after that, it's false again. So now our AI knows exactly when an episode has ended and can use this information to help to better train. Awesome. I think we can get rid of that. Close the script again. Close the terminal. And what we should also do is to go back to our live manager and set the lives back to 3. I think what could also be done to clean this up is to get rid of those 2 lines. We have never used them. And in the script, we should of course comment the prints out again. Awesome. We will finally create the graph for the random agent. For that, we go to the MyAI controller, and under InfoSet counter, we can define a new variable. This variable will just hold the points of the current game. This will follow the same pattern as before. We just send the game score from the Space Invader game to the AI controller. And then in the getInfo function, we just need to write 1 line of code. Info dictionary for Python. Then we create a new key. In-game score. Make sure the spelling is correct. Otherwise, the PPO script or the NTPTR script won't know where to get it from or how to get the score. Equals in-game points. Awesome. Then of course we need to find the script in the main game that deals with the points. If you want to search it by yourself, you can pause the video now. And otherwise, it's just the points counter here. So open the script, and then above the ready function, we just import our AI controller the same way we always do. And then it's pretty simple. We just go to the increase points function, and we use this points variable to override the respective variable in the AI controller. So, which is this one. AI controller dot in-game points equals points. And what is also missing is that if the game restarts, then our AI controller still holds the points of the game that has ended before. So we want to reset them, which is pretty easy. We just copy this into the ready function. So when the game is restarted, this whole script is executed again, which also means the ready function is executed, and which then sets the points to 0. Otherwise, we would have 1 or 2 frames where the points are the points from before, not 0, and this can be avoided easily. Anyway, we are now ready to generate the graphs. So make sure, if you click on the sync nodes, then you are in the training mode and have a speed up of 10. and everything is saved. And then you can go to export the game again. So the settings should just be the same as last time. Make sure this is true as long as imgui is still in the game. And then just override the executable from before. Then you can open the terminal, activate the environment if you don't have to, and go into the path. I think from now on I will stop saying it or repeating it. And then we can type in Python, the name of the script, then environment path, then the path to the executable, and then number of environments 6. You can also try it with more, but more on that at the end of this video. Hit enter. And then wait until everything has popped up. As I mentioned before, the terminal is printing a lot of things because for every environment, it is printing all of the information. Okay, this is looking good. What we can do now is to open our weights and biases. Then in projects, if your project is called test Space Invader, you can click on it. And then click the eye on the topmost training run. And you should already see that the moving average game score was populated with a bunch of games. If you click on runs, you should also see a run like this. So we have provided the random word and we have a lot of 0 rewards and action repeat 4. And it's only running for like 2 minutes for me. There are 2 things remaining that we need to talk about. The first thing I want to mention quickly is also noted in the description of this module. It is about how many games your hardware can run in parallel. I haven't really found a perfect way to deal with this yet, but currently my best approach is to start with a high parallel count and decrease the number of games until the training stops crashing. Maybe as a very rough rule of thumb, you could say that if 16 gigabytes of RAM equals 6 executables, then one executable needs about 2.7 gigabytes of RAM. So if everything so far worked, then the crashing should be because of memory or hardware issues, if you started the training with too much game. For me, this often occurred after about 1 hour of training, because then the terminal said something about leaked RID and also showed other issues. That probably occur because the games are fighting for the hardware. I already mentioned the second thing in the tracking experiments with weights and bias module. In there I had described that the graph that you see here on the left was produced in about 9 hours. However, I think the tendency of the random agent is also very clear after about 13 or 15 minutes, which shows the graph on the right. So tracking 9 hours of data was way too much. I just did it because I can, and because I think it's interesting for the course. I probably mentioned it way too often by now, But overall, the random agent serves just one goal, which is to get a baseline number we want to beat. In Space Invaders, it's about 400. But if we want to be a bit conservative, we can say that in order to beat the baseline, we need to score at least 500 on the average of 200 games. So the 425 you see in the description will be updated. If you're dealing with a different game, then you can just treat the highest peak of the random agent graph as the baseline. If you're more curious about the exact numbers on the graph, feel free to read the description of the current module. Which is this one. That's it for this module. If your random agent ran for about 15 minutes, then you can quit the training by pressing Ctrl+C in the terminal and then look at your graph and maybe find its peak. In this module, we will give the real agents control about the game. So in the MyAI controller, the first thing we can do is to disable the random agent. So just go to the variable and set it to false. So then this warning will go away. And then we have to take care of the setAction function, which is pretty simple because the Python code is sending the action the PTR or PPO algorithms are choosing via this function. So this action variable already contains a number between 0 and 3. We can quickly have a look at the corresponding code. So in the getActionSpace function, we already set the size to 4 and the action type to discrete. And then in the PPO script, the neural network knows what the output should look like because of this line. So environment, single observation space, shape. So this is where it takes the output range from. And similarly in the PTR script, basically the PTR code is also using the same thing from the environment, which is even better visible at the line 1600 when we input the environment.singleActionSpace into the agent initialization. Anyway, the only thing that is important for you is that if you set this correctly, then the action that will come from the Python will be correct. So we can use it. Changing the code now is pretty simple. I would say we just remove the not. Then we move this line that generates the random action into the if random agent. And maybe even change the variable name to just action. So then we can overwrite it here and overwrite it here and get rid of the pass. And I think we have to get rid of the variable definition to remove this error. However, if you print the action variable that is coming from the controller, it will actually look like that. So it is a list that contains the variables and then the numbers. So what we want from the list is just the integer, in this example, the 1. The easy fix for that is that if we are not using the random agent, then we want to have an else statement and actually use the action variable instead of overwriting it. So we will write action equals action and access the variable. And what we can also do, just to be sure, is to convert this into an integer. And then finally, we can get rid of the next error, which is just the about this else statement here. So we can just move the if action equals 3 to the left, alongside the other else statement. Awesome, I think we can test the training now. So open the terminal and type in Python, PPO script and track false. And then of course press the play button in the Godot engine. So this looks good and this looks good as well. So it's of course hard to judge from the game that we are not using the random agent anymore, because PPO at the start is also completely random. But since we set the random agent here to false, we don't use this random function anymore. So it kind of has to be the PPO script that is sending the actions. Now we can deal with the rewarding of our agent. Since later on our first agent will be called 1_PPO, we can already write that in the reward dictionary. So instead of the random, we just write 1_PPO. We can also write the numbers for the rewards. We will talk more about them in the module of the first agent. But game lost will be just -1. Life lost will also just be -1 for the first experiment. And game won and alien shot will be 1. I think we will first focus on the coding and do the main explanation afterwards. So let's jump right in to the getReward function. In there, we can get rid of the assert comment and define a new variable that will hold the total rewards for the current exchange that is sent to Python. So variable total equals 0.0, and the decimal is important because later on, when we have float or 0.5 or so rewards, then we don't want them to be rounded or so. What we can also do is make some space and return our total variable. But we will clamp it. what the clamping is doing is if the total variable equals 2, for example, then it will return 1. If it's -5 or so, it will return -1. But if it's in the range -1 to 1, it will just stay as it is. We clamp the rewards to this range because PPO prefers this range for its rewards. The next step would be to go up to the rewards dictionary again, and under it define a new variable, which is just another dictionary. So we are collecting rewards from the game, not at every frame, but also at 4 frames in a row or 8 frames in a row, depending on your action repeat value. More on that later, but we need a dictionary that kind of gathers the rewards of the current exchange. This dictionary is also nice to visualize the rewards we get. So we can actually go to the imgui and print it in there. What we could also do is to print if the random agent is activated. I kind of forgot that before. So if random agent, then we just do imgui dot text wrapped. Attention agent the AI not learning anything. And by the way, you can always Google the full screen on the upper right. Then I would scroll right to the end of the function. And we can copy that. And instead of the shooting allowed, we just write this AI steps reward. Then imgui.text. And now I would call the stringify function from JSON in order to visualize our dictionary properly. So we take this AI steps rewards and provide it with the indent string, just some empty spaces. And we don't want to sort the keys. Awesome. This should come in handy later. The next step would be to write a function that can give us the rewards from the game. So above the getReward function, we define another function. Give reward. Write a type hint. And it will return nothing. So we send it to the void. In there, we just use our dictionary, this AI step rewards, and then make a new key. which is the source, which then will come from the game itself. And here we will use the source function, because it can happen that in the first frame we get a reward from shooting an alien, but in the third frame we also get another reward for shooting the alien, and then in the fourth frame the reward is summed up and then sent to Python. So we want to actually add these rewards together that are from the same source. It's kind of unlikely, but it can happen. And it's even more likely to happen if you increase the action repeat value. These are step rewards, get, then the name of the source or the key, and the default value if there was no entry before. And then we also add the value of the respective reward from the dictionary. So if it's game lost or game won, we just take the value from there and add it. What I should also mention is that now it's not so relevant that we add the reward that we already had with the new reward together, because 1 plus 1 is 2 and gets clamped to 1. But later on, if we have 0.1 times 2 will still be in the range. So later on, this will make more sense. All right, the next thing we should do is to actually find the 4 places in the game where we can get the rewards from. I think we can start with the alien shot reward. So if you go to the main scene and look into the game, we can search for the place where it would make the most sense to grab this information from. So the information is that we shot an alien. For example, the points counter would be relevant here. But in this game, maybe I should just show it to you by going into the human mode and resetting the speed up. So in this game, not every alien is giving the same score. The red one gave 0 score, but I think that's normal for Space Invaders. And currently, I'm not finding an alien that is giving not a score of 10. So you maybe have to just believe me. I think that was more. Okay, that was definitely more. You could, of course, give different rewards for different aliens. But since we want to keep it simple for now, we will not use the points exactly for the rewards, but just information that we shot an alien, which we get from the increase points function. So since we already imported our AI controller here because of these 2 lines, we only have to add 1 line in here. AI controller, give reward. This is calling our function we defined before. And then we provide this thing, however this is called, and our key from our rewards dictionary, which is alien shot. Yes. All right, let's quickly test if all of this worked. So we can activate the training mode and then start the Python script with the track false, because it's just a quick test, and then start the game. So the agent is shooting aliens randomly, and we get the reward. However, the resetting is of course not there yet, so it's just adding and adding. Normally, this should be resetted every 4 frames, or whenever the action repeat value says. But this is looking pretty good. Okay, so now you know how to reward the agent. I think we can make an exercise to deal with the other rewards and then to visualize it in imgui. So you don't need to write any imgui code. You just need to find the places where you want to grab the information from the game for game lost, life lost, and game won, and then call our getReward function, giveReward function, the same way we did in the UI. Not in the UI, in the points counter. And then if you start the training, you should see the respective rewards. So you can pause the video now and try it for yourself. And I think doing these exercises will help you to really learn what's going on. So after this course, you will have an easier time if you want to train an AI for a different game. Okay, so I hope everything worked out. If not, that's no problem. It's good that you tried. Let's first start with the reward for the game won. So you probably found it, I think. It's the best place is the game won function in the UI. So in there, we already imported our AI controller for something else, but we use this import. So at the start of the game won function, we use the AI controller, then our function give rewards, then the AND operator, and the respective key. So the remaining rewards are in the live manager. You can also just type it here as always. The first thing we need to do here is to actually grab our AI controller. I will just copy paste the line, since it's always the same. Then we can go to the onPlayerDestroyed function and just below the lives, but I think it doesn't matter, lives -1, we can write AI controller dot give rewards And then we just write our life lost key. And in the case our lives are 0, so if lives not equal 0, we have this code, and otherwise if it's 0, we just give the reward for the game lost. So currently what will happen here is that if we lose the last life, we get a -1 reward. And then we also get a -1 reward because we lost the game. So we get a reward of -2, which doesn't really matter because in the AI controller, we clamp the reward to the range -1 to 1. And if we have different rewards, it is still nice to have a bigger reward for the very last life. So in order to test the things that we have written, I think it would be best to make some temporary changes, because game 1 will be quite time intensive, and also game lost is also a bit time intensive. So the first thing we can do is to go to the live manager and temporarily change the lives to 1. And then in the player script, I would just overwrite the match and training words. So we want the human controls to be activated when we are in the training mode. And when we are in the training mode, we don't want the AI to control the game. So just write something else here. This should give us control about the agent, even though the training mode is activated and it's connected to the Python script. We also need to do this change in the shooting script. So just copy the original lines and comment them out. And then the training will be something else, and the human will become the training. Awesome, now we can test everything quickly. So go to the console and start the training with the track force. Then press play in the editor. And yeah, test everything. So since we have 1 life, we should now get a life lost and a game lost, which is good, but I also want to test it with independently. So let's set this to 100. Awesome, now we get life lost -1 if we lose a life. And -2 if we lose another life. I will also try to win the game, so we see the reward for winning the game. But I think I will speed this up a bit. Okay, that was rather quick, but we got the game 1 reward. And I shot like 55 aliens, now 56. And I also lost 3 lives. But since I had 100, it doesn't matter. Awesome. The only thing that is missing now is to go to our AI controller, and in the get reward function, we need to actually move the rewards from our this AI step rewards dictionary into the total rewards variable, which is pretty simple. We just loop through every key in the, or every value in the dictionary and add it to the total. And then we reset the dictionary so it's empty again. We can also test this quickly. So now the rewards are immediately reset. I think I already did most of the main explanation, but let's quickly go through what is happening. For that, I would go to the AI controller and the sync node and reset the speed up to 0.1. Maybe you can still remember this slide. So we have the Godot game on the left side and the Python script on the right side. And every 4 frames or 8 frames, or depending on the action repeat value, which basically controls the reaction time of the agent, we regularly send or do some exchanges. So let's say every 4 frames, we send game screenshots, rewards, and so on to Python. And then Python sends back an action and other information. So every 4 frames, one of these exchanges is happening. So on every exchange, we just send one reward number that may consist of all the different rewards that we can get in the game, and kind of summarize if the current situation looks good or not. For example, if we shot an alien but lost the game at the same time, this would cancel out to 0, so we would get a 0 reward, which is not ideal, so we will change the reward shaping later on. But if we only shot an alien and nothing else happened, then we get a reward of 1. And so on. And of course, after every exchange, we reset this single reward value. So this is why we summed up all of the desired step rewards into the total variable, and why we reset the dictionary and the total variable on every exchange. But to make this really clear, we can also visualize it. So in the PPO Python script, we can search for .step. So on line 395, we find the exchange Python code. And then we can decomment the print variables. And don't forget to save it. And don't forget to decrease the speed up to 0.1 and set the mode to the training mode. If we now start the training with the track force and our manipulated Godot code with the 100 games and so on, lives and so on, everything will move in slow motion. And you also see that the rewards are 0 all the time until I shoot an alien, which will take a while, but otherwise you wouldn't be able to see it. So we hit the alien now, and then there was a reward of 1, and on the next exchange, paused it, and on the next exchange, the reward disappeared because we reset it. And what we also see here is the game score that is also sent in the infos. Okay, I can't. I can continue the game after pausing it. So and now, if we lost a life, we should see it in the imgui over here. I think after the animation is finished. Which maybe make it harder for the eye to learn. So in a game where the animation take even longer, you could take care of that. So the -1 on the left side, let's pause it again, was visible for one exchange. And I didn't look at the imgui. I hope it was there. I think you have to press enter in the terminal, then it continues if you also press continue here. But that's it. So I will not win a game or so again, because this will take forever. But we can maybe show the rewards for shooting the aliens. And now I saw it. Okay, we can close all of that. Awesome. So the last thing we will do in this module is to revert our changes in the player script and the shooting script. So let's get rid of this line and this line, and then decomment the training and human keywords. And also do the same in shooting script. By the way, I'm pressing Ctrl X in the respective line. And Ctrl hashtag on the German keyboard to decomment several lines at once, or comment. And also in the live manager, 3 lives are enough. So you don't need to, but if you start the training now, the PPO agent should take control of it again. Oh, and maybe you can reset the game speed as well. Now we can give our AI agent some eyes instead of giving him black screenshots. So then the getObservation function is sending real game screenshots. This whole process will involve several things, and most importantly, a viewport. This is just the Godot component that allows us to take screenshots from the game with the engine itself. In order to do that, we need to open the main scene of the game and click on the main node to add a child node beneath it. Then we can search for subviewport. Normally those things are used, so the subviewport and subviewport container are used for minimaps, portals, portal-like things, split screen, and other useful stuff. However, we will just use it to get the game screenshots in a very performance-friendly way. So first we add the container, then under it, by pressing Ctrl A or the plus on the top left, we can add the subviewport. And I would also drag it right below the main node. So then you have the viewport in the middle of the game, which is okay for now. The first thing we can do now is to click on the subviewport and change the resolution size of the image to 84 by 84. This is important because an image that has like a resolution of 1000 by 1000 is way too much data for the AI to handle. It could of course handle it, but then it would like, I don't know, take 100 times longer to train, or we would need much bigger hardware and also a bigger neural network. So currently, if we activate the human mode and go back in the main node to start the game, the subviewport isn't doing anything. In order to change that, we can attach a script to the main node. So click on the main node and then above it, click the plus icon. The name is actually fine, so we can just create it. Okay, so the first thing we need to do is to import some things. For that, we write on ready variable game viewport. So the type hint is a subviewport, and you could spell that out, or you just drag the subviewport from the main scene in here. So because the subviewport is a child of the main node, we can import it easily this way. The next thing we need is of course the camera. So main camera, the type in is a camera 2D. And you can type it or also drag it to get the path. Then we can import our AI controller. So for that, we just go into one of our scripts. and copy our AI controller input line. So as soon as the game starts, we want to connect our viewport to the AI. So for that, we write the ready function. And I will write the code and explain it afterwards. Game viewport dot world 2D equals get viewport and world 2D. Then we define a new variable, which is just sub camera, which equals a new camera 2D. So camera 2D dot new. And we can also write game viewport dot add child and includes this sub camera as a node. In Godot, the scene tree is executed from the bottom to the top. So as soon as the game starts or is restarted, the main node is executed, which then runs all of the code together with the subviewport. And then all of the other stuff is happening. And I think in order to understand what is going on here, it is best that we explain what a world 2D is in a bit more detail. So a world 2D is something like a central data container and manager that is responsible for the interaction of objects in the game. For example, in a split-screen shooter game, you have one world with different players. But each player needs its own viewport to see the world from a different angle. So player 1 gets one viewport, player 2 gets another, and so on. But they all look at the same world, so to say. So you can also think of the AI as just another player that views or looks at the world of your game. And in our case, we want the AI to receive the exact same images that the player receives, which is why we add this new viewport, and we will then copy basically or connect the camera of this new viewport to the camera of the game. So they see exactly the same thing. However, before we continue the coding, let's quickly start the game to see what is going on. So you might see that those aliens do not belong in here. They are just from the viewport. So if we click on 2D and on our container, then we can click on the move mode or just press W so we can move it around. So this is the thing we saw here. And by the way, another reason why we use the container is so we can move the viewport around. Because if we only use the viewport and not the container node, we can't move it around. So later on, we will move it outside. So this is not visible, but for now, it's nice to see what is going on. Because the next step would be to actually downscale this image so it shows the full game rather than one big invader. So what we do now is to get the main viewport and the sub viewport and calculate kind of a zoom so the image looks better or actually shows the full thing. Variable main viewport size. Yeah, and we also need the sizes of the viewports to calculate this zoom. So get viewport.size. And we can copy this line because in here we just change it to game viewport and get rid of the brackets. And then of course this will be changed to sub viewport size. Awesome. To give our camera the correct zoom, we just write sub camera, then access its zoom property, then access the main camera zoom property, and multiply it by sub viewport size divided by the main viewport size. I think I can toggle the full screen now. If we now press on the play button to test this, we see that the image looks good now. So this is the image that the AI will receive, which shows the full game. And by the way, the Space Invaders game has of course a fixed camera. In more complicated games, you might need to change the code, but Godot RL Agents also provides a camera sensor. I didn't know about them before I came up with my own solution. So if you're dealing with a more complicated game, you could try them out. So the 2D camera sensor and the 3D camera sensor. I think my solution is doing pretty much the same thing, but it might be worth a try. I think I can close this now. And by the way, I can also give you some code that might be helpful if you are dealing with a different game. So you can play around with it if you might need it. So most of this is just syncing the properties to match the properties of the main camera's view. And a few other things. The last thing that is missing here is to actually call our AI controller and give it the viewport or access to the viewport. This follows the same philosophy as the rewards or other things we send from the game to the AI controller, rather than the AI controller asking the game for it. So back in the controller, in here we have of course to provide the variable for the game viewport. So under the 0 observation, we just write variable game viewport. Next up, we go to the get observation function and write if not is instance valid and provided the game viewport. Then we just return the 0 observation. Doing this is just another safety measure to increase the stability. Because sometimes when the game is reloading, we may have not connected the viewport yet. So this is not a valid instance. And in this case, we just return a black image. For similar reasons, we can do another safety measure. For that, we define a new variable. Let's call it texture. Then call game viewport dot get texture. And if we don't get an image from the game viewport, which means the texture equals null, we can also return the 0 observation. Then we can give the actual image to the AI. For that, we define a new variable. Let's call it img. It's an image type. It gets an image type hint. And then we do the texture dot get image. And we can also convert the image to black and white. So in Space Invaders, this of course doesn't matter because the game is already black and white. But in other games, this saves quite a lot of data. Because an image that is black and white needs less data than an image with color, or with color channels even. So image.format underscore L8. So I don't know what luminance is, to be honest, but this just turns the image to black and white. If you can remember it, the black image or 0 observation was converted to a string before it was sent via networking to Python. And Python then converts it back from the string to numbers. This is done because that way the networking is faster, since it's kind of a bottleneck in reinforcement learning sometimes. So we will just do the same with our image. So we will convert it into a string, and then Python will convert it back into numbers. Doing this is pretty easy. We just define another variable. Let's call it observation string. And then get our image that is already black and white. Then get data. And then call the function hex encode. So this is basically serving the purpose of converting numbers to a string. Then the final step would be to return the observation string, which will also get rid of the error down here. Oh, and maybe you noticed that I forgot a tiny thing. So we were turning the string, we were moving the string into a dictionary. So we need to do the same with the real image. So we can just do dictionary observation and then give it our obs. Awesome. In the next module, we will test all of this by actually saving the screenshots and looking at them. The best way to test our code is to visualize the images. For that, we open our PPO script and we can search for the step function to deactivate the prints from the last module. Then we can close the search and go to the top of the script and search for the save PNGs variable. If you set this to true, then all the codes that are already prepared in order to visualize or save the images will be activated. So for example, this will create a folder that is named Visualize AI Inputs, in this folder where the project lives, and it will do some other things. So if you set it to true, you can save it and go back to the game. In the Godot engine, we have to make sure the control mode is in training, and we can also increase the speed up to 10 before opening the 2D view in the main scene. And in there, we have to move out the subviewport container. Otherwise, our agent will also see this in a minimized form. So click on move mode and just move it anywhere outside the rectangle. Then save everything and start the training. So we will just start the training with the normal command for testing by providing the track false. But before you start it, you can zoom out quite a lot. You will see in a second why. Then hit enter, and in the engine also hit enter. Awesome. I think you can recognize this image. So I just started the game in the normal player mode and paused it. You can perfectly see the bunkers here, and you also can see the player, as well as the invaders. But don't wonder that the invaders look a bit strange. This is because we are looking at the downscaled image. So all of that is 84 by 84. But if we wouldn't have downscaled it, we would have something like 1000 by 1000, which is of course way more data. For example, every 0 is a black pixel, and every 255 is a white pixel. So we would just have way more of them. But we don't need to, because the exact shape of the aliens does not matter. Maybe if there would be a special alien hidden inside of them that we want to catch, then it would be problematic. But there could be other workarounds for this, rather than increasing the hue or size of the image and therefore increasing the data amount. It can happen that in your terminal this doesn't look perfectly. So this is because the terminal is a bit weird in its behavior sometimes with the zooming and the scrolling. So don't wonder if it's a bit different. Anyway, we can go back to the game and end the run. We should have enough images by now. So if you open our folder, there should be the Visualize AI inputs folder with a bunch of images. In my case, it's like, I think 100. But it could be that it's always 100 independently of how long you run the game. If we open our first image, then on your PC, it might be zoomed out, and you can just zoom in. So this is looking pretty ugly compared to the normal game, but as mentioned before, our AI doesn't care about it. As long as it can recognize the player and the bunkers and the aliens, and the aliens don't increase or decrease in the size. So as long as the collision shape of the aliens is the same as the visual shape, which should be the case, then it's fine. And on the upper left, you can see that this is the first image. If we quickly scroll to the images, we basically can see that the number goes up to 100 and everything is moving. If you wonder what program I use to view the images, it is this one from the Microsoft Store, OnePhoto Viewer. This works pretty nice to view images quickly, but you don't need it, of course. Maybe you already recognized that we have 100 images that just show one screenshot of the game, but we also have another 100 images that always show 4 screenshots of the game. Let me quickly arrange that differently. Perfect. So on this slide, I mentioned that one exchange between Godot and Python sends one game screenshot, which is kind of right. One exchange is sending one image. However, we are not sending the image you see on the left, we are sending the image you see on the right. So one exchange is sending exactly one image, but this image is showing 4 screenshots of the game rather than just one. The reason for that is explained pretty simple. Let's just look at the left game and search for an image that shows a bullet. Perfect. So if you only get this image and have no idea about the game, then you don't know that this bullet is moving down. Even if you have some idea of the game, and this bullet were on the left side, so not above a bunker, this bullet could be from the player. So if you just look at a single screenshot, you don't see any movement. But if you look at more screenshots, and we talk about the blinking of everything later. So let's go to the 50 image and then look at the player, and then I increase the image count. You see the bullet comes from below and goes to the top to the player. But you also only see this if you're looking at more images than one. Which is exactly why the eye receives 4 images at once. So you can also imagine all of these 100 images to be in one video, and when I increase the image count, it's like I'm pressing on the play button. So let's do that, because now this image doesn't tell us anything really, because there is no bullet moving. So if I search for an image with bullets, then this is a perfect example. So maybe you saw it already. We have in the image name stack 30, 31, 32, 33. The images here are in the same order. So on the first image, you see a bullet that is a bit above the bullet on the next image. And the bullet on the next image is even lower. Or should be even lower. But in this case, it's true. Maybe I also have to mention that this image is not exactly what the AI is receiving. So the AI is receiving a stacked image. I just showed the images side by side, or created the images side by side in order to visualize it and to explain it. To understand what the neural network is exactly receiving, we can have a look at this image. So if our AI agent would receive an image like that, he would basically get the thing from the terminal, which is the matrix. So then you can imagine there's a 0, there's a 0, there's a 0, there's a 0, and there's a 255 or something. But if it's getting the stacked images like that, then every game screenshot is kind of one layer in this tensor. So you can just think that our AI neural network is receiving a tensor instead of a matrix. To explain this in more detail would, I think, explode the scope of the course. But I think you can just Google neural networks and convolutional neural networks and matrix and tensors if you're more interested in that. If not, that's not a problem. In this module, we will deal with the blinking of the rockets and improve the quality of our screenshots, so they are a bit less noisy. Let's start with the viewport settings. You will find them and you click on the sub viewport. So the container also has some settings, but we want the sub viewport settings. To be honest with you, I just played around with them until I saw what I liked. So we can go through them rather quickly. The most important settings, 84 by 84 for the screenshot size, are already done. So the next one is we disable the 3D rendering. Then we can click on Snap 2D vertices to pixel. And in the rendering, we can set the MSA 2D to, I believe, 2 average. You can also enable the TAA. And then in the SDF section, we can set oversize to 100%. This is explained rather simple. So 100% basically means the oversize is deactivated because we show 100% of the rectangular of the viewport. But if we have 110 or 120%, we just draw a bigger rectangle around our viewport rectangle, so to say, and show this as an image. Finally, we can set the scale to 100% because this just controls the quality of the image. Alright, now that this is done, we can start a new training run to see the difference of the new images. But before that, I would go to the folder with the images from before and just rename it to something differently. But before that, make sure that the lives in the live manager are set back to 3 and the sync node in the AI main is on training and the speed up is at 10. Then just press the play button as always and go to the terminal to start the training. So this was the old folder and we also have a new one. And once it's filled up, we can just go to Godot and stop the program. Okay, let's open the folder side by side and also open the first image in each folder. So with the current settings, you don't see much of a difference. However, if you, for example, look at this invader here and invader here, you clearly see a difference. And also if we, on the left, scroll through everything, the invaders change their shape extremely. And on the right, if we do that, the invaders also change their shape, but they stay a bit more consistent, which should help the AI to learn a little faster. I think playing around with the viewport settings is only really relevant if you want to get out the maximum of your hardware and of the AI algorithm you are using. So there's just a trade-off between speed and performance and also quality. For example, if we go to the Godot settings and we would set the rendering MSA2D to 8, which kind of says slowest. Then you would get the picture on the right. And if you have it disabled, you would get the picture on the left. So on the right, you could see the invaders way better, and they are also way more consistent than on the left. So you could try this. Maybe this will decrease the training time. But I don't know how much the performance cost is. So I would have to do some experiments on that. However, I think in Space Invaders, it's no problem if we use the picture on the left or the picture on the right. So don't worry too much about all of the viewport settings. Anyway, let's deal with a more important issue. So you may have noticed when scrolling through the images that sometimes the rockets are disappearing or blinking, so to say. So if you scroll through our images, we pretty quickly find an example of this. So on the first stack, we see every rocket, and on the next stack, one rocket disappeared, and then another, and then even the next one. But soon after that, it is reappearing. This issue was very present in the first set of images, but after playing around with the viewport settings, the issue got less dominant. So if you scroll through the improved images, then the blinking or disappearing of the rockets should be less noticeable. For example, on my stack, starting with the number 20, there is a rocket, then in the next frame it's also there, and in the next frame it suddenly disappeared. And also in the first frame it was missing. This is of course a big problem for the AI, because the rockets are kind of the main challenge in the game. And since the AI always receives a tensor of 4 images or screenshots, we kind of need some consistency for it to learn properly. I quickly opened a screenshot of our terminal where we debugged the image in order to explain, I think, the reason for the disappearing of the rockets. So the first thing is the downscaling of the image, of course. And the other thing is that the rockets have a very tiny width. So, for example, if you look at the bunkers, you see that the right bunker has 2 0 columns and the left bunker has 1 0 column. So if our rockets have a very low width, then it makes sense that sometimes they just disappear because the image gets crunched. So in order to deal with this, you could play around more with the viewport settings, which is kind of tedious for me. or you could increase the image size, which is not good for the eye. So I will do a different solution, which is just to increase the size of the rockets. So in the Godot engine, we have to find the alien and the player sprites for the rockets. By the way, finding out about the rocket disappearing issue took me quite some time, because it is a silent error and it decreases the training performance and speed, but it doesn't completely ruin it. So this is why we debug the images or look at them at close detail, so we can kind of spot those things in advance rather than overlooking them and then searching the problem somewhere else in the pipeline. In order to find the sprites, you could search through the whole game, or you could just do a little trick, which is to start the game, shoot and pause, and then open the remote tab and click on the areas. So don't want this. I guess this is also not a rocket, but this is the rocket. And then if we found it, we can just open the scene and close the game. And there it is, we found it without searching through our whole game. We can then do the same trick for the player bullets, but I think setting the speed back to 1 makes this easier. So just start the game, shoot, press pause, and then in remote tab. It's not this area because this is from the invader. So we can go into the main, and then maybe under the player, there is nothing. But if we scroll down, then there's a laser, which is the thing we're looking for. Then click on open scene and stop running. And if we zoom in quite a lot, we see our laser that the player is shooting. Okay, let's start with the invader shot. And on the left, you see an area, a sprite 2D, a collision shape, and something else. What we want to change is the sprite 2D. Because this is just the image that is shown. But we don't want to change the collision shape, since this would kind of change the balance of the game. So if you want to debug the collision shapes, you can always go to the debug at the top and then toggle on the collision shapes. If we then start the game, we see all the collision shapes of every object. So for example, the invader don't even have a perfect collision shape. If we click on Sprite 2D, we can then go to the transform and change the scale of everything. But before that, let's just make it ridiculously big to show you the difference between the collision shape and the visible image. So there you see the collision shape, and there you see the rocket. If we now start the game, the rockets are hitting us, but since the collision shapes are not hitting us, there is nothing happening. So if I find a collision shape, I get destroyed. Anyway, we can go to scale and unlock the chain, and then I think the value is 5, and 3 work quite well. Then save it. And now it looks a bit better. But I messed up the collision shape. So I just revert anything until the sprite is above the collision shape. And then we can click on the sprite again and type in 5 and 3. And now we see the collision shape is inside the sprite. And everything should work properly. Awesome. By the way, if you don't like manipulating the appearance of the game, you can probably make use of the visibility layer. So what I think should be possible is that you have on one visibility layer, you have a rocket that is normal, so the human sees it, and on the other visibility layer, you have a rocket that is big, so the AI sees it. Then it looks fine for the normal human player, and the AI can also work with it properly. You could argue that the downscaling of the image is kind of making it harder for the AI anyway. Let's go to the laser and do the same thing. So on the sprite 2D, we go to the transform, and then we just type in 7 and 3 to make it a bit bigger. Save the game and quickly test it. Awesome. What we can do now is to toggle off the visible collision shapes and then test what we did. So in the AI main scene and the sync node, we can set the training mode, increase the speed up, and then just start our training. And maybe before that, we need to delete the images or rename it, however you like. So then it will take some while until 100 images are generated. And we can corrupt everything. So let's just click on the first image. And then we should see very big rockets. Awesome. And this is a good example because on this image, you see one rocket is very big and the other rocket is very small. Which now doesn't matter because the rockets are always visible and our AI doesn't get bombed out of nowhere. Maybe here we can see it even better, but I think the point is clear now. And for example, if there's a rocket in one screenshot or stack, then it's also visible in the whole stack. And the blinking fully disappeared. In this module, we will take care the graph for the moving average win-loss ratio. And by the way, the moving average reward does not show any graph or numbers, because if you can remember, when we created it, we just had a bunch of zeros in the reward dictionary in order to not confuse anything when dealing with the random agent. Let me quickly open the graphs of the agent I already trained and prepared. So we already talked about this. This is the first PPO agent we will train. And there you can see that the moving win-loss ratio, which by the way is an average, it's just wrong in the title, is already filled up. Creating this graph is not strictly necessary. However, I think looking only at the points is a bit boring. And you want to know how often your agent really wins the game. So in Space Invaders, 1100 points or shooting 55 aliens wins the game, at least in our Godot implementation. The original Atari is a bit different. But it's just good to know how much games our agent is winning exactly. Which is kind of messy to see in the average game score graph, but it's really obvious in the win-loss ratio graph. Let's quickly recap how this graph works. So if you take exactly one data point and have a closer look at it, so on the x-axis, we see that it's at 211 million. And on the y-axis, it's at 0.065. So the important thing here is that this one data point is the result of 200 games, because it equals the average win-loss ratio of those games. Which means if we have won 20 games and played 200 games, then the win-loss ratio is 0.10 or 10%. And if we have won 14 games out of 200 games, then the win-loss ratio is 0.07, which is exactly or almost the ratio we have here, and probably ratio of the peak of this graph. Which is of course not really good, but it's just the first agent. The other ones will get way better. If you want to calculate the number of games the agent is winning when looking at the graph, for example, you would just see the 0.07, and you would take this number and multiply it with 200, and you would get the 14 games. Maybe I should also mention that there is a tiny difference between weights and biases and the PPO script. So in weights and biases, the sliding window of 200 games is 200 games, but in the terminal, we also print the moving average win-loss ratio from time to time, but there we don't use a window of 200, but we use a window of 50. However, this difference is not so important. It is just there because when we look at the terminal, we are a bit more interested in the very current situation of the agent performance. Anyway, enough talking around. Let's open the Godot project. In the my controller, the getDone function already sends the information if the game has ended, but it is not sending the information whether we won or lost. And since this signal is basically a Boolean and can be nothing else, I think, we will just send the information within the getInfo function. So the important thing here is that we make sure it is also only sent once for one frame or one exchange and not several times in a row. Let's go to the process function. And we will utilize the code for restarting the game in here. So under get pending true, game pending true, we can write one lost pending true. This will help us to get the information for exactly one exchange. Then we need to define this variable. So let's just copy that and call it one lost pending. Then in the getInfo function, we can make some space and do something similar than we did in the getDone. So if one lost pending, we set one lost pending to false immediately. And in the other case, we pass for now. The code we will write here will in the end set the value in the infodict for Python. So let's copy that and move it up. And I just code this information busy lost one. So the variable will also be called busy lost one. And it will contain a string that is either busy or lost or won to tell Python whether we won or lost the game. To get rid of the error, we can just define the variable at the top. I would place it right here. And set it to busy. The next thing would be to find out if we lost or won the game. I did this by looking at the lives left and the alien shot. But if there's a better way, you can of course do it differently. So if lives left and aliens shot, this will be a new dictionary containing this information. So remaining lives. If the remaining lives are 0, then we know busy lost one has to be set to lost. And in the other case, when lives left and alien shot has an alien shot value of 55, we set busy lost one to 1. So in our case, it's 55 aliens. In your game, the winning condition might be different. Now we can define the dictionary at the top. Let's place it below the busy lost one. And make sure the keys are spelled correctly. I hard-coded the values here because I don't want to change them anyway. But the more clean way would be to use an onReady and just get the values from the game. Now we need to go into the game and actually set the lives and alien shot values in the dictionary with the current values of the game. This works similarly as every time when we want to get information from the game to the controller. So we find the respective place, use our AI controller import, and then get the information. So I would say you can pause the video now and try it for yourself and just make an exercise out of this. So the first thing is pretty easy to find. We just go to the live manager, and there we already imported the controller. So we can write a process function after the ready function. And we don't need the delta, so we can place an underscore in front of it. And then we just call AI controller dot lives left and alien shot. Take the remaining lives key. And use the lives variable. And maybe you have even thought of the game restarts. If so, then this is pretty nice, because when the game restarts, the remaining lives are kind of set to 0 for the first exchange before the process function is entered. So we just set it to 3 immediately, because they are set to 3 once the script starts. This is maybe not even necessary, but it's just more clean to do it that way. Then I would say we can just copy that to be lazy and go to the main scene of the game. And then in the invader spawner, go to the top and just insert what we have written. So the controller import, then there's already a ready function, so we don't need it. We also don't need that. And this has to be moved into the ready, as well as into the process function, and then of course changed. So we want the alien's shot key, and we will use the invader destroyed count. So which is increased here whenever an invader is shot. And set to 0 at the start of the script. So let's copy this line and go to the process function, which is not there, so we just write it. Awesome. Now we should be able to see the information when we start the training. Before we can test all of this, we have to get to get info function and set the busy lost one to busy in all other cases. So when we don't won or lost the game. Then I would say we just print the lives left and alien shot dictionary, which we can do in our imgui function. So let's just take this, copy it, and then write lives left and alien shot, and also stringify the dictionary. Then I would go to the live manager, because we don't want to wait until all 3 lives are lost, and set it to 1. And in our Python PPO script, we can of course go to the top and set save PNGs to false. We can also search for the step function. So around line 400, we can decomment our 2 prints, which are printing the reward, the terminated truncated stuff, and the information dictionary. So then save everything and start the training. So make sure the training mode is activated. Then press play. And now we already see the busy lost 1 is 1, which is wrong. So, and what we also see, we have 1 life remaining. We have shot some aliens, and the key is wrong. So we have alien shot and alien shot. So let's open the Godot engine. Press the stop running project button and fix the error. If you press Ctrl, Shift and F, and then we can type alien shot, we find every usage in the whole project of this string. So AI controller give reward alien shot is correct, and alien shot in the rewards is also correct, but in lives left and alien shot, we have defined it wrong. So let's just place an S there. And you could also search for the lives left and alien shots and see all the places where we use them. This is also how you could have found the issue. But I think every other place is looking good. Or not, I placed the S at the wrong place. So it's aliens shot, not alien shots. I also noticed that I made another mistake. So in the get info, we of course have to set the busy lost one to busy in the case we neither lost nor won. But a bit of failing forward doesn't harm us. So let's start the training. And now I hope it should work. Awesome, so we are busy. And then we lost the game. And let's pause it. So you can look at the score. And there you see we had a score of 80. And we're pretty busy all the time. But once we lost the score, we were still busy. So there's still another error somewhere. And if we look at the game, we see alien shot 6, lives left 1, which doesn't tell us anything. Okay, I looked at everything and copied the important outputs here. And I think the reason why I got confused is because in my ground truth project, I debugged everything with a 1x speedup. And here we debugged it with 10x, which may be the reason that the behavior between my old and the new code appeared to be different. I think it's because we have some racing conditions in our code. But don't worry too much about it. It's not that big of a problem. So the racing conditions in the code are likely between the normal FPS and the physics tick rate. So some parts of the code react differently to the speedup than other parts. So I marked the important parts here. We have the reward of -1 when we lose the last life. And we also have the done signal. So terminated, truncated, it's basically the same thing. And it's both true for one exchange. And the third thing, we have the busy lost 1 information with the lost info. So those 3 things could be on one line in an optimal code or perfect code. And then we have also the fourth thing, which is the change from a game score of whatever, like 450 to 0. Ideally, this change would happen right after we get the done signal. So the game is done, and then we get the game over. And in my ground truth code, those 2 things, or even all 4 things, happened on the same line, which was kind of changed by or revealed by the 10x speedup. Anyway, there are a lot of things going on in the code, and getting this perfect can be very tricky. So I skipped it because our goal is to train an agent and not to do too much optimization side quests. That said, AI training probably benefits from frame perfect information. So future courses will have a closer look at those things, if I find the time for that. What remains to do now is to test our graph for the moving win-loss ratio and also look at the average reward graph to see whether the rewards appear there. But since an untrained agent will not win the game, we have to do our trick again, where we hijack the AI controls and use the human controls instead. So just copy the original lines and decomment them out. So this one will not get used anymore temporarily. And this one will be used in the training. Then we can do the same in script after saving. Copy that and then change training to something and human to training. Awesome. Then make sure the speed up is back to 1x and we are in the training mode. And then we can start the training. But this time use the weights and biases. So we started without track force. So let me lose a game first. And by the way, I think I will speed this up again. And I also hope this is the last time that I have to win the game manually. Okay, this should be enough. Let's have a quick look at the terminal before we look at weights and biases. So in here we see that all the information talked about earlier is on one line. So we have the reward of 1, done signal, we have the 1, and then we also have the score of 1100 on one line, and then on the next line the 0 score. Which kind of confirms the things regarding the racing conditions and the 10x versus the 1x speed up. We can also observe this here. So here we have a -1 reward and the done signal and the lost, but the game score was not reset for one time, but then in the next line it was reset. Perfect, we can see that everything worked as expected. So we got some reward and it is shown on the graph. And we also won a game, so the win-loss ratio is not 0 anymore. It is pretty low because we calculated with 200 games versus one game, but that's not a problem. To end this module, we will revert the hijacking of the controls. So just delete those two lines and decomment those two lines. Then in the player script, we can do the same thing. And everything works normally now. Here is a quick overview of the agents that we will train in this course. So this video on YouTube contains the 3 parts of the 101 course. So we will do 4 PPO agents and 1 BTR agent. On school, there is the rest of the 101 course. It will contain at least 2 more BTR agents, but maybe even more. And this will not be the only course that you get on school, since this pipeline isn't a dead-end setup. So what I mean by that is best shown on the school roadmap. The 101 course kind of represents the first level. In there, we learn the basics of the pipeline by training an AI in Space Invaders. Level 2 is about applying the AI speedup in high speed. Since we have discussed a lot of the details about the pipeline in level 1, we can take more of an overview approach in level 2 and just overall do it in a faster manner. For level 3, I probably won't create a course. The idea is that you learned enough in level 1 and 2 and can ask questions in school. Of course, you don't need to do it, but if you want to pick an open source Godot game from YouTube or somewhere else, then just go for it. Level 4 is kind of the big goal of all of this. It's similar to level 3, but here you create your very own game or training environment in the Godot game engine. However, it will maybe get its own course, since we can also do advanced things like, for example, cloud training, curricular learning, or having multiple agents in one game, and so on. Since we're talking about experiments, we also need to talk about hyperparameters. In machine learning, those are just some numbers, like a learning rate or exploration rate, that you adjust to tune the algorithm. However, dealing with them can be a very complex thing. So this course will not deal with them, and we don't even have to, because the hyperparameters we use for PPO and BTR are already quite good for a lot of environments. To add a bit more details to this, the PPO parameters work already quite okay for like 30 different Atari games. And the BTR parameters perform superior for even more Atari games. And more importantly, we also solved Super Mario Galaxy, Mario Kart, and Mortal Kombat on a Wii emulator. So we basically have the choice between adding a few hours more to this course or quickly gambling for some gains in performance. Therefore, I just use reward shaping and ditch the hyperparameter tuning, since in our case it gives us a way bigger leverage on performance anyway. And it's more fun too. All of this leads to the nice thing that you don't have to deal with machine learning details if you just want to train an NPC for a game, as long as it's not something totally different than the games we talked about. Here is a nice little overview of the Atari games. And there you can also see the original implementation of the Space Invaders game. But keep in mind that the score works very differently from the Godot implementation, because in the original games we had waves, and in the Godot game there is only one wave, which you could change, of course. I also have some additional notes on hyperparameters, but feel free to skip them, it will get a bit technical. The point here is that the number of agents you train influences some of the hyperparameters. This means if you are not using 6 environments in parallel or 6 agents, you can change the parameters a bit to improve the performance, since this is a low-hanging fruit. All you need to do is to change one value or maybe 2 values, and these values will come from the table 1 I already prepared. And as a side note, the bigger leverage on improving the performance is probably the training time, but changing the parameters a little bit can also help. So as an example, let's just say the number of environments or agents you were able to train on your hardware is 7. Then you would look at the table, search for the num-envs and then 7, and then just take the num-steps value, which is 146, and change it in the PPO script. So in PPO, you can search for a number of steps, find this line, which is right here. And then you would change this value to 146 and save the script before you start the training. But of course, I will keep it because on my hardware, I can only run 6 environments in parallel. However, if everything works with more than 8 environments, you can use the second part of the table 1. Because then the number of steps value stays fixed at 128, but you have to change the mini batch size value, which can be found right here in the PPO script under the number of steps value. There you just change the default. If you're more curious about the parameters, then you can check out this table. So in there, I compared the original parameters from the PPO paper with the cleanIL papers from the framework we are using and the parameters we are actually using. So this is what the PPO paper looks like. If you want to read more about it, you can click on View PDF to open the PDF. And there you would also find the table 5, which I used to copy the hyperparameters from. Anyway, I also thought about going deeper into the formulas, but it would take a lot of time, and I'm not comfortable enough with them yet. So all of this may not be without any errors, but I tried my best to get it as right and simple as possible. The Python script kind of always saves a model if you started it without track faults, because I decided to only save models if voids and biases is used. So whether your PC crashed, or you interrupted the training, or it finished, you should get a saved model. The models will be saved besides the scripts, but I put them in a folder, so it's a bit nicer to see. So the model always has the ending pth, and normally it's called checkpoint. This is the trained model of the first PPO agent, and for the PTR agents, it's kind of similar, but it's like in a nested folder, and there you have the checkpoint file. And some additional things that need to be there, but can be ignored. Anyway, this executable is probably out of date, so we can go to the project and quickly update it. So let's say we want to continue the training of the first PPO model. Then we would just go to the terminal, activate everything, you know the drill, and then type in Python, the name of the script, and the environment path, and the number of environments you want to use, and most importantly, the checkpoint command with the correct name. So in our case, this would be 1_PPO. Then you would just hit enter and see all of the normal things that pop up for the training. And the training should be continued in voids and biases. If you want to use the trained model without Python, that's totally possible, but it requires a few extra steps that won't be covered in this tutorial. The most important point for that would be to export the model to a different format, which is the ONNX format that the Godot engine can use by itself. Anyway, if you just want to look at how good the model is without resuming the training, you could just set the number of environments to 1. So everything loads a bit faster or starts a bit faster, and provide the track false argument. Oh, I provided the wrong path for the model. So it's in the trained models folder. So we just go to the command from before with the arrow keys, for example. And then we can write a backslash and trained models. Now it should work, but don't forget the track equals false. And to set the number of environments back to 1. And you should also provide the right name of the model. Okay, nice, finally it works. And now we can see the trained TPO1 agent, which only had a 10 or 7% win ratio. So don't wonder if it's not the best player. Okay, I think we can interrupt this by pressing Ctrl+C in the terminal. Then there are a bunch of errors that don't matter if we cancel the training itself. So let me write CLS. You could also reset the speed up to 1. So in the sync node, just here, and then watch it at normal speed. Just don't forget to re-export the game, or you'll start it from the editor. We can also talk about the PTR script, because continuing the model training or looking at the trained models is basically the same thing. The main thing you need to consider is to provide the right path to the checkpoint. So we just have the Python command that starts the PTR script. Then we have the environment path. If you want to start it from the executable, you could also just hit play in the Godot editor. We want to use one environment anyway. And then you have the checkpoint, which for me lives in the trained models folder. Then one BTR, because it's the first BTR agent. Then this path with the 200 million and so on. And then the checkpoint and the track false. It also says here, resuming from checkpoint. And it also shows you the steps where the model was at. Anyway, you could also use this to play against your own AI if you are in a different game and manipulate the code a little bit. By the way, I haven't tested PTR without using an NVIDIA GPU yet, but quickly watching the PTR model could work even without a GPU. But that's it. If your training gets interrupted for some reason, you know how you can continue it. And I think I just had to do this for 1 or 2 agents, even though I trained way more. Alright, let's finally start the training of the first PPO agent. Since I spoiled him already, you should probably know that these rewards are not perfect. But I chose them because setting every reward to positive or negative 1 can be a nice idea if you have a more complicated reward structure, or are not too sure about the balancing. Okay, before starting the training, make sure that in the sync node you have set the speed up to 10, the action repeat to 4 if you want 4, and the training mode. And then don't forget to export the game. Before you open the terminal. Starting the training is pretty easy. You just use the Python script, provide the path to the executable, and then choose your number of environments. I go with 6 on my hardware. And then you hit enter and should see a bunch of things. As I mentioned before, these rewards and all these commands for information will pop up once for every agent. But it's always the same information, so it does not matter. All right, the training has started. And you see that there are a lot of windows. You can move them around however you like. And if you're wondering why we show those windows, it is of course possible to hide them during the training, but I haven't taken care of this yet. So what you also see here is that we connected to weights and biases. So on the platform in our own project, or in your project if it is called test Space Invader, which is the default, you should already see the graphs. And if you click on runs, you should also see the name of the agent, the rewards, and so on, and that it started 6 minutes from now and is running for 2 minutes. This may be a little bit faulty, but it's no problem. And then you also see the hyperparameters and a lot of other stuff. By the way, in the terminal, you also see this thing. This is just there to show you the temperature of the computer and the hardware usage. So if you're pretty near on that, it's good. But if you're too near, it can mean that your PC is about to crash. So make sure you watch this if it crashes. And here you see the peak is 60 degrees. So to that I can say that if you put something under your laptop, if you use a laptop, then the fans have more room to breathe. And doing this reduced the training temperature for me by like 5 degrees. So this is from the training start, but it will also pop up during the training from time to time. And if the training pauses, that means you'd have to hit enter. This is only because I clicked around in the terminal. So how long should I let this run for? We kind of discussed it already in the module for the random agent graphs. The goal we discussed there was to train an agent that clearly beats the tendency of the random agent, which in our case is a moving average score of 500 points. If you're using 6 environments, then this should be achieved in about 2 to 3 hours. But if you want this PPO agent to win some games, it will take quite a while. For me, it was really about 2 days, because I had a low agent count. So for practicing and debugging, I would focus on clearly beating the random agent. And if you want a really good agent fast, then I would focus on the BTR algorithm. And the cool thing about all of this is that you can watch your agent train live via the weights and biases platform. You could even watch this on your phone. I think on Android you have to open it in the browser, but if you have an iPhone, there is also an app for this. Anyway, I will end the training early because I already trained the first agent, as you know. But I will also upload the model of this agent so you can look at it as we did in the module before. So you would just go in here and provide the model here and the drag force, and then hit enter and hit play in the Godot game. To see a trained model. Let's discuss the next agent. I already mentioned that having a bunch of ones is not the optimal structure. So I would change the values to that. And the reasoning is that maybe losing a life should be less penalized than game over. So life lost is minus 0.1 instead of minus 1. For the second reason, we need to compare the game lost reward and the alien shot reward. So losing the whole game is kind of nothing compared to shooting all of the aliens. Because if we shoot 55 aliens in the perfect case, we get a reward of 55. But if we lose the game, we only get a negative reward of minus 1. So to force the agent to take game over seriously, we just reduce the reward for shooting an alien to 0.07. Then 0.07 times 55 is about 4. So game over roughly costs 1/4 of the max episode reward. And I also think that losing a life should not be the same as losing the game, so I also reduced that. All we need to do now, before starting the training, is to change the reward dictionary, and the rest will stay the same. So this is the second agent. Game lost stays the same. Life lost is reduced to 0.1. And make sure you don't forget the dots, so it's a float. And game 1 will stay at +1. And alien shot will be changed to 0.0. Don't forget to save. Awesome. With that, we just need to export the game so the new rewards are used, which is pretty fast anyway. And then we can use our command to start the training, which will spawn a bunch of instances and connect to weights and bias and so on. Perfect. We also see the rewards everywhere. And here's our new agent. However, I already trained him for way too long. So I can interrupt this. And have a look at the different agents. Let's have a closer look at the beginning of the game score graph. So this greenish line on the top, ending with the number 411, is the first agent. And this reddish line or brownish, ending with the number 180, is the second agent. This graph only shows the first 2 million steps. We will walk through the full graph, which has 230 million steps. So the second agent here seems like a total failure because it has like score of 350, even though our random agent has a score of 500 or 450. If we jump to 30 million, then we see that from 2 million on, our agent 2 got way better. However, agent 2 is still below agent 1, so it's still not that nice. Then, if we jump to 55 million, we see that agent 1 loses the 500 score and kind of gains it back. So it stays better than the baseline or the random agent, which is not shown here. And agent 2 kind of improves a bit in the overall tendency, but also stays very weak. I quickly added the graph for the random agent, which is the purplish color that ends with the number 613. So you see the numbers here. And remember, it is not learning anything, so it doesn't matter that it's cut off by 20 million. It could also be cut off by 1 million or even earlier. Anyway, if we jump to 86 million, then we see that our agent 2 kind of exploded. It even got better than the agent 1, so it has like a score of 700, while agent 1 only had a score of about 550. This could be because the agents need to learn to see while also learning to play the game. So it could be that agent 1 just had an easier time doing that, but once the agent could see and really had to learn to play the game, the agent 2 had an advantage, and maybe this is the reason because it kind of exploded then. But at 166 million, we see that agent 2 lost his advantage, while agent 1 kind of gained it back. This already hints kind of an imbalance in the rewards, because our agent 2 is jumping around a little bit too much, without a consistent, clear tendency of progression. So I would say the progression of agent 1 looks way more healthy, because it's jumping around less. Anyway, if we look at 230, which is 100% of the agent I trained, we see that agent 2 kind of achieved the same outcome as agent 1. So agent 1 has like a score of 900. So it's a moving average game score of 200 games. You know that by now. And agent 2 has like 830. But I would still say that the weird graph of the second AI is not optimal, even though it could be that he would outperform agent 1 on this graph with more training. Let's also have a look at the win-loss ratio graph. It tells a bit of a different story. So this is the agent 1. At its peak, it had like a moving average win-loss ratio of about 6% or maybe 7%. But the agent 2 had a win-loss ratio of about 18% at its peak and ended with 16 or 14%. So it's way better. In fact, it more than tripled the win-loss ratio of the agent. What this means is that out of 100 games we let both agents play, the agent 1 would only win 6 games, while the agent 2 would win 18 games. And there's also another interesting thing about this graph. If you look at agent 2, it starts to win its first games at about 60 million steps, while agent 1, I think, only starts about 135 million. So if you look back to the moving average game score graph, our explosion happened at around 60 million, which is exactly when we started to win some games. So our agent really improved its skills there. So if we look at both graphs side by side and go to where the agent 2 started winning the games, which is at 59 million on the right, we also see the 59 million on the left, which is where he exploded. And what we can also do is to look at the first winning of the agent 1, which is around 30 million. And if you look on the left, there is also a marker, which is exactly after the jump of the first agent. We could also have a look at the reward graph, but in our case, this is the least interesting graph. And if you wonder why the lines look very different from the agent 1 and the agent 2, this is because we're using very different reward structures. And maybe you could get some insights from this comparison between the two lines here in the reward graph, but it's kind of tricky and not necessary. You can also look at the agent by loading the model I already trained. But don't worry if you don't see any difference between the PPO agents, because when they don't perform extremely different, you can only see the difference with statistics by analyzing thousands of games, which is exactly what we're doing with weights and biases. So without the graphs, we would have a hard time realizing that we more than tripled the win-loss ratio of our AI. When analyzing agent 2, I mentioned that the graph had no stable increase, but that it still looked promising. So I think the ideas behind the numbers are good, and that we should just change the balancing of them a little bit. Alright, let's change the number to 3. Then the life lost can be minus 0.9, and this time it is correct. And we can also change the alien shot to 0.2. Now the positive signal for shooting an alien is way stronger, and the negative signal for losing a life is way stronger as well. Okay, now we need to do just one thing before we can start the trading, which is to export the game. So the new rewards are used. Then we can open the terminal and start the training, which I won't do because I already trained the agent. Okay, we have again cut off the steps at 2 million to look at the first part of the graph. So if you can remember, the most right graph, ending with the number 411, is the AI1 or agent 1. Then we have the 180, which is AI2. Then AI3, which is ending with 347. And then on the left, we have the random agent. So the second agent performed really badly at the first 2 million steps, while AI1 as well as AI3 look very similar to the random agent. This is a really good sign for agent 3. However, if we look more closely on agent 3, we see that it has a clear upward tendency, beginning with a score of 350 and ending with a score of 420, I think. If we look closer at the first agent, then we don't see such a tendency. But to be fair, in the end, both have a score of about 420. So overall, agent 3 already looks quite promising. Let's jump to 20 million steps. So up until 16 million, AI3 leads the race. But then it quickly loses to AI1. By jumping to 79 million, we see that agent 3 is catching up again, leaving AI1 behind. Then on 142 million, we see that AI2 crashed and AI3 still had a clear upward tendency until 142 million. So AI1 is currently the best one. However, by jumping to 196, we see that AI3 has recovered and progressing even faster than AI1. So I have to say that I regret cutting the training of the agent 3 a little bit, because it would have been really interesting to see more progress, but I cut it at this point. I think it's like 3.5 days. So if you look at the full graphs of all agents, then we see that agent 3 was the best one. So it would have been interesting to see it progressing even further, because it had a clear upward tendency the whole time. I think it would have done quite good. But it's also way faster than the other agents to reach a score above 900. Because the other agents, even after 5 days, didn't reach it, but would probably have for some more training. So I had to make some stops, since training multiple agents for days is already a bit over the top. So if you're really interested in training PPO agents, you should increase the parallel agent count somehow. We already discussed the options for that in earlier modules. However, I just wanted to figure out what's possible with minimal resources and a very simple pipeline. Let's look at the moving win-loss ratio graph. Agent 3 wins its first games around 160 million. So the second agent won its first games before Agent 3. And at 196 million, Agent 3 achieves a ratio of about 16%, which is really nice if you consider that it was way faster than the second AI. Anyway, here is the reward graph, but we will skip it again. This graph would be very interesting if we did hyperparameter optimization instead of reward shaping, because then each agent would have the same rewards, but for example a different learning or exploration rate. Reward shaping acts like a translation layer between the game and the AI. So if you want to tell it missing shots is bad, we have to translate that into a reward. Otherwise the AI has a hard time to pick it up. Now, the agent isn't completely blind without one. It can still connect the dots over time through credit assignment, but that connection is weak and delayed, and it costs the agent complexity to figure out. A direct penalty saves him that work, freeing up brainpower for other challenges in the simulation. This isn't just theory. The BTR paper hit a similar issue with Mario Kart. Agents often neglected using the item, since there is no direct link between action and reward. So they just motivated the AI to use more items by giving it a reward for using them. Back in Godot, we can change the experiment name to 4_PPO and then add the missing shot penalty. So shot missed. And let's choose 0.02. So if you multiply that by 10, we get the reward for shooting one alien. And I think missing 10 shots per alien sounds like a reasonable balance, since we don't want our AI to get afraid of shooting. Okay, all we need to do now is to use our give reward function within the Space Invaders game to give it this reward. By now, we have done this a lot of times, so I think this is a perfect time for an exercise. So the cool thing here is that if you add the function in the game, imgui will automatically print the respective reward because the give reward function stores it in the this step rewards dictionary, and this gets printed in the imgui. So you can perfectly debug it. Okay, so a common way bullets work in games is that they get deleted after shooting them. Because if you don't delete them, the performance could decrease because over time there are just too much of them floating around in the game memory. Therefore, there is something like a bullet catcher to delete them, which is this thing. The way it works is quite simple. Let me quickly go to the sync node and go into human mode and reset the speed up. So if a bullet hits the top, it gets deleted instead of floating around outside the game. So whenever we don't hit an alien, we hit the bullet catcher and the bullet disappears. But there's also another way we can miss hitting an alien by shooting, which is shooting the bunker. So this is the second case we need to take care of. If you want to find the code that we need to touch, then you can remember the trick with the pausing of the game and then clicking on the remote bar and then on the laser. So then you see the rectangle here. So you can confirm this is the right thing. Then all you need to do is to go into the game, press Ctrl, Shift and F, type in laser and find all of the occurrences in the code. So we don't care about this. We also don't care about this. But what we care about is the bunker part and the bullet catcher. So here's the bullet catcher and here's the bunker part code. Both of these codes, check if the area is in laser and then Q3 them. The alternative way to find the places that you need to touch is to go to the main scene of the game and then click on the bullet catcher and click on the open editor and then on the script. Or just directly click on the script. And for the bunker, it's similar. Ah, there's the game. You just click on a bunker and then open the scene. And then you click on the script. Don't be confused. All of the scripts are just pointing to the same code. And there you would also find the respective function. Okay, the first thing we need to do is to grab our AI controller import. Then we go to the bullet catcher script and import the AI controller. After that, we can just go into the if area is laser. And call our AI controller. Then give rewards. Got missed. And that should be it. If we now start the game and miss some shots by shooting the bullet catcher, we immediately see we get the shot miss penalty. And by the way, don't wonder if the rewards don't disappear. They only disappear in the training mode and stay consistent here in the human mode. Awesome, but if you shoot the bunker, we don't get the shot missed. Okay, next up we go to the bunker part. And this is a little bit more tricky because the area that has entered the function could be a laser, but it could also be an invader shot. So let's quickly import our AI controller. And then just add the reward down here. So if we start the game now, and I don't even shoot once, we see that the invader can give me a negative reward because they missing shots or shooting the bunkers, which we don't like. So let's add an if statement here. We just check if area is laser. We give the penalty. I do it this way because I don't want to mess around with the code here, since it's pretty easy to accidentally mess things up if we don't look close at it, which we don't need to. So let's just do it this way. If we test it now, we see that the aliens can't give us a negative reward anymore for shooting the bunkers. But if we shoot the bunkers, we get a penalty. Or if we hit the bullet catcher at the top. Awesome. Now our agent can make use of the penalty and will hopefully learn to stop just spamming the shoot button and focus a little more on his aiming. We already added the penalty for the missing shot in the previous module, so you can start the training right away. I will skip this again since I already trained the agent. So let's have a closer look at the first part of the graph. Okay, by now you should probably know that weights and biases is presenting the agents in order here. So this is the first PPO agent, this is the second, third, fourth, and this is the random agent. I think I will quickly turn off AI 1 and 2, so we can clearly see the graphs we are more interested in now. Okay, that's way better. So agent 3 and 4 look almost identical. Since the only difference is a tiny missing shot reward. But the unexpected cool thing here is that 4 was even a little bit better than 3. And it's also a little bit less fluctuating. By jumping to 30 million, see that AI4, which is this one, is quite similar to AI3, but it seems like it's winning the race until we look at the very end, where it's quickly falling down. However, at 58 million, we see that AI4 quickly recovers and even starts to outperform AI3. And if you can remember, around here at 58 million, AI2 exploded to a score of about 650. Anyway, at 140 million, we see that AI4 falls down a bit, but it stays above AI3. If we jump to 100% of our graph, then we see our poor AI peaked at 160 million with a game score of 850. So maybe it has risen too fast, but jokes aside, I have no idea why AI4 crashed like that, but I'm very curious for your ideas. By the way, I don't think that these two artifacts here are at fault. These are just occurrences from the interruption and continuing of the training. But since after the first artifact, the training seemed to do quite well, I don't think that the second artifact caused the drop in the performance. Anyway, let me quickly go to the run sections and activate agent 2 and 1 so we can see the full graph of all agents. So this is agent 1, AI2, AI3, AI4, and the baseline. What definitely is a factor in the training is the drastic increase of difficulty. So, for example, it is quite a different challenge to shoot an alien if there are over 40 of them. Then it is to catch one if there are less than 15. The very important thing about that is that the eye is confronted way more often with easy situations than it is with hard situations. So the training data does not support winning often. There are solutions to that, but those would explode the scope of this course. Anyway, let's go back to our graphs and deactivate the first and second agent so we can better see the moving win-loss ratio. I think it's really interesting to see that AI4 started winning games way earlier than AI3. I would argue that penalizing missing shots helps the eye to get more precise and therefore perform better when there are less aliens. Anyway, after its downfall, our AI4 stopped winning games. But it was quite an interesting experiment. So maybe changing the size of the penalty could stabilize everything. Or we could introduce it after, for example, at 100 million steps, or if a certain performance threshold is reached. This means it would learn the basics without the penalty, and then we increase the difficulty. Things like that are called curriculum learning, and will be added to school somewhere in the future. I can also show you the reward graph. So if any of those graphs would be interesting, then it would be this one, because the reward structure is completely the same between AI4 and AI3, except for the missing rocket penalty. However, if you want to see the full reward graph of all PPO agents, then it is here. So we could do a bunch more of experiments with PPO or just jump straight to PTR. PPO was quite nice to explain and test everything since it's hardware friendly and popular. However, to get real performance without much hardware or hassle, we will jump to PTR. PTR follows the same idea as PPO's older cousin, which is the Rainbow DQN. But most importantly, it basically achieves state-of-the-art performance on consumer hardware. So unlike other very strong algorithms, it can easily be used by normal people. How PTR learns? PTR keeps a buffer, which is a memory bank of past experiences. It keeps replaying those memories while it plays. So PTR is basically an overthinker, half living in the present and half still dreaming about old moments. So, because of the buffer, a lesson from way back can still shape what it does right now. Switching from PPO to PTR is pretty simple, since our pipeline is modular. We just swap the PPO Python script for the PTR script when running the training command in the terminal. So whatever worked for PPO works untouched for PTR. There is only one tiny addition in the MyAI controller needed. And I needed to drop the n-parallel count to 4, since PTR needs more resources, which is no problem because it's still superior. Alright, back in the Godot project, we can first move the random agent flag up, because we will add another flag for the PTR agent. Let's just call it training with PTR and set it to true. Then we can change the experiment name to 1_btr and set the short missed reward to 0. Since the first experiment will not use it. Okay, I would say let me code everything and then explain it. So all we need to do here is to go to the getInfo function and just send a bit of additional information to the PTR script. So I would say above the info send counter, we just add if training with PTR, then info dictionary for Python with the key ignore, and the restart game pending variable. This is the first information we send, and the second information is quite similar. We just set the key to first. All right, that's it, because handling the info dictionary for Python is already done quite well by our code that we wrote for PPO. But everything that works for PPO in the script also works for PTR, since everything is quite modular. To explain this a little bit, let's go to the top and toggle full screen. So whenever you want to use the PTR algorithm, you have to set this flag to true, since it's sending ignore and first flags over the network. Because the PTR algorithm expects those flags. So the purpose of them is not perfectly met with this code. Because the way this is intended is that if you have a game that takes a longer time to reload and to restart everything after the game over, then we want to skip these frames, because the AI can't do anything with them. So immediately after the game over, you would send the ignore flag, and then when the restart of the game has finished and the first frame that is relevant is sent to Python, you would send the first flag along with it. However, since our game reload happens quite fast, I just chose to send the same variable for both of these flags. So this stuff isn't really doing much. And by the way, the restart game pending variable does the exact thing that is sent as the get done signal, because we have to set it for one frame only to be true. By the way, using the restart game pending variable works quite well, because the sync node is always calling the getInfo function before it's calling the getDone function. And therefore the ignore and first flags are always only true for one change. So in the sync node, we can look at the training process function, and there we see the getInfo function is called, and then a little bit after that, we call the getDone function. Okay, what remains to be done is to test this. So what we will do is to go to the live manager, set the lives to 1, and set the training mode and the speed up 10. Then in the PTR script, which should be at the same level as the PPO script, we can search for environment.step, which is around line 1674. So all we need to do here is to outcomment the print statements. So we can look at the info dictionary. Then you just save the game and open the terminal. In there, we just write Python BTR 101 with the track force and without any checkpoint or executable. Then we hit enter and also start the game. And wait for the agent to lose. Awesome. Okay, now we need to find the needle in the haystack. What I would do is to just select everything with Control A, then copy it with Control C, and open Notepad or something. If you then insert it, we can search for the bracket with the -1 and the dot. So we find the negative reward where the agent lost a life. And quickly after that, we should also find the ignore and first, which show the true values. So what you could also do is to search directly for first and true, but make sure the apostrophes and everything is correctly. In this case, we got the negative reward in the first exchange, then another exchange, and then we got the first true exchange. So the first true is only true for exactly one exchange, which is what we wanted to see. So we can confirm that this worked. However, the ignore false is wrong. So it's never set to true. And if we look at Godot, then we see that I made a typo. So the ignore is now uppercase, and the first is also uppercase. Okay, I will quickly run this again, so we can see whether it worked now. Awesome. Now we see that we got the ignore true and also the first true on exactly one exchange. And on the exchange before and after, we get false. With that, we can go to the terminal and interrupt everything. And also in Godot. And then I would go to the live manager, reset the lives back to 3. So we can start the training run. Let's start the first PTR experiment. So first, make sure the training with PTR equals true. And then we can export the game. And override our executable from before. And also make sure that the shot missed reward is on 0, 0, because we want to use the best rewards of our PPO experiments. We should also make sure that in the PTR script, we outcomment these two lines around 1679. Because we're not debugging anymore. And save the script. By the way, if you're in weights and biases and click on one of your runs, and then go to overview, you can see the exact comment that was used to run the experiment. which is the same we will use here. And if you connected everything to GitHub, you can also see the exact commit, so everything stays really reproducible. All right, in the terminal, we just use this command, Python btr101, and then environment path. Then there's our executable, and then I use numenvs for. Because on my hardware, I can't use 6 environments, since btr takes a bit more resources. Let's hit enter to start the training. And the behavior of the btr script is basically the same as the PBO script had. So for example, I just copy pasted the monitor function. You see the output here. But the big difference is that btr needs to fill its buffer with memories before the real training starts. So I think for me this takes like 30 minutes and almost needs all of my 16 gigabytes of RAM because it's storing compressed observations. You can watch the peak RAM usage in the hardware monitoring output. For me, I already used almost all my RAM, even before the real training started. This is because I have a lot of open programs. So I would recommend to restart your computer before any real training run. That way you can ensure that you get the most out of your hardware. And this output is also shown or printed during the training. I think like every 40,000 steps or so. So it should pop up again soon. Anyway, if the training crashed and the peak RAM usage was almost at 100%, I would recommend to decrease the buffer size up to 10% before trying it with less parallel environments. You can change the buffer size in the btr script. Here you can search for class space agent, and then you will find the max memory size. So I already changed the value to 960,000 because the original value was like 1 million and a bit. So if your training crashes, I would just decrease a little bit and then try it again. But the annoying thing about this is that you have to wait for the buffer to fill up, which can take half an hour if you only have 4 environments. But once you could run the training for 1 or 2 hours, you should be safe and you should have found your personal and parallel value and buffer size value. By the way, if you have more than 16 gigabytes of RAM, then you can probably use the original buffer size of 1 million and a bit. But I think going above this brings no real benefit. So try to stay as near to this number as possible. I should also mention that on my hardware, the game windows freeze periodically after the buffer has filled. This is not a problem, it's just because the algorithm is calculating updates. So don't worry too much about it. Now there are already some more hardware monitoring outputs. So on the first one, we see that I used 14.9 gigabyte of my 15.4 available gigabyte. Then after that, it decreased a little bit and then a little bit more. But the peak still shows this 14.9, which is really close to 100%. So I expect it to crash in 10 or 15 minutes. So maybe I will wait for that. By the way, what's shown here are just the 12 virtual CPU cores. And So this line means that they do quite a bit of work. If it would be an exclamation mark, don't worry. And this just means the respective core is almost used to its full potential. And it's a dot, then it means the core is not really used at all. And there is also things like the read and writing speed that is currently on the disk happening on the disk, and other stuff. Okay, half an hour has passed, and you can already see that the game freezes really periodically. I think it's freezing even stronger and more often and longer than it would do if I had restarted my computer. We can also see the FPS drop from 177 to only 40. Which probably means that my training will crash soon. Okay, I let the AI train for the whole night, because to my big surprise there was no crash. Maybe this is the case because when developing everything I used Godot 4.4, and it could be that Godot 4.6 is just more stable. Or it was just luck, I don't know. Anyway, here you can see that the training ran for about 21 hours and that we already have a win ratio of 98%, which is quite nice. When we watch the agent, we can probably see him win the match, even though my computer is not so happy about it. But as long as the training works, this is no problem. Let's have a look at the agent I already prepared. So this is the PTR agent, and this is our random baseline. And here it looks like the PTR agent is quite similar to the random baseline. If we look to about 2 million steps, see that the agent is slowly starting to learn how to play the game and increases its score. If we jump to 2.6 million, we see that our agent reaches the 500 score and gets even higher. By jumping to 3.1 million, we see that our agent has a really good time and even reaches a score of 800 almost. Then on 3.6 million, we see that our agent reached a score of 1077, which is almost the max score he can achieve in the game. So if we jump a bit further, we see that he's reaching basically the max score. Still not. Almost. Okay, let's just look at the full graph. Then we see he stays there until we end the training, but he also achieved 1100 quite a lot, which is because we have a high win-loss ratio. And by the way, this is still the moving average game score graph. So every point, like this one, represents the average of 200 games, which means at this point, at 8.3 million steps or so, he won 200 games with a perfect score, because otherwise he couldn't win. Let's look at the graph for the win-loss ratio. So here we see that after like 2 million steps, the agent starts to win some games. And then after 3.6 million, he's at 90%. And then he slowly climbs to 1%, 100%. And he even reaches 100% sometimes, which is the 1, but he has a hard time staying there. So overall, he's pretty good, but he can't win constantly for a long period of time. And in case you want to see it, I can also show you the moving average reward graph, which is kind of boring. Okay, I hope you learned a lot, and I'm already very excited to see the things you will do with this pipeline. If you want to watch the remaining modules, check out my school. I will also upload more courses there. Thanks for watching, and don't forget to touch some grass.